how each of those methods of aquaplaning caused the aircraft to lose direction on the ground because the aircraft was being lifted away from the tarmac, either skidding along on water or the reverted rubber build-up of steam lifting the aeroplane, and obviously that's all going to have a detrimental effect. We looked at the minimum aquaplaning speed. What was it? 8.6 times the square root of the tyre pressure in PSI. Definitely highlight that one. That one comes up quite often. But if you see the 8.6 times, there's your clue, your warning lights going on. And we finished off there. We finished off with aquaplaning. So we've done wheels, tyres. Yeah, we've had a look at aquaplaning, and now we're going to move on to the different types of undercarriage that we might come across. Yeah, each type of undercarriage leaves its own footprint. Yeah, the size of the wheel depending on the size of the aircraft, and obviously the bigger the aircraft, yeah, the larger the wheel would have to support the aeroplane, and the larger that wheel becomes, the more difficult it's going to be to stow in the aircraft. So what we can do is reduce the size of the wheels, but increase the number of them. Yeah, so we end up with different types of gear. We have the single wheel landing gear. Yeah, standard single wheel. It's got fairly limited load distribution where the wheel sits on the ground, and the size of it is limited as well. So what we can do is reduce the size of the wheels, but increase the number of them. We can do that using the tandem gear, where one wheel's in front of the other. Again, we're sharing out that load distribution now, or we can use the double wheel, where the wheels are side by side rather than fore and aft. And again, we can see the load pattern, sharing the load out a bit more. And then for your much larger aircraft, yeah, smaller wheels, yeah, but more of them, yeah, and that becomes your buggy type undercarriage. Yeah, and again, the footprint of the wheel is, or the footprint of the landing gear is spread out a bit more. Yeah. Wheels, I wouldn't worry about this because it varies from aeroplane to aeroplane. But just when we're talking about the wheels, depending on the size of the gear, we need to know which wheels that we're talking about, so that they are numbered or identified in different ways from different aircraft. With something like the Jetstream, which is dead easy, yeah, it's either the nose wheels or the main wheels. You can't go far wrong with that. But if you're looking at something like I don't know, 777, where you've got 6 wheels on each bogie. If I say, "Oh, go and change that main wheel, would you?" Yeah, you think, which one? I've got a choice of 12 here. So we need some means of identification, and that identification method will depend on the aircraft type that you're working on. So you could have 1 front, 2 front, yeah, 3 front, 4 front, 1 rear, 2 rear, 3 rear, 4 rear, or you could have 1, 2, 3, 4, 5, 6, 7, 8. However you want to do it, whatever the method is for your particular aeroplane, it just means that we get the right wheel when we're talking about it. Your standard single wheel that we've already mentioned, yeah, your old tricycle undercarriage, but you've got your single wheel, the double wheel, yeah, the side by side, double wheels there. The tandem, yeah, it took me ages. Believe it or not, I was looking for a picture of a tandem undercarriage when I was doing a a class in Sudan, and it took me ages to find one, and the only one I could find that showed the tandem undercarriage was on I think it was a Danish fighter aeroplane. And one of the students there said, "Oh, well, what about the C-130?" And I've flown on them hundreds of times, and I never even realised that the C-130 had the tandem undercarriage. Yeah, strange what your every day's a learning day. But this little Sudanese guy, well, what about that? Oh. And yeah, right enough. Yeah, 10 out of 10 to the guy. Perfect example of a tandem undercarriage. And then we go on to the bogie. Yeah, the big stuff, where we're going to reduce the size of the wheels. Yeah, but put lots of them on, all increasing what they call the footprint, the contact area with the ground. Yeah, but the wheels are a lot smaller, easier to manage, easier to handle. So each undercarriage, single wheel, double wheels, tandem wheels, bogies. Yeah, and the type of undercarriage unit governed by the weight of the aircraft and the strength of the runway on which it operates. So it says multi-wheeled undercarriages. A lot of smaller wheels instead of a big, large wheel. Lots of advantages there. Easier to stow when they're retracted. Yeah, it says they provide greater safety. If you get burst tyre, yeah, because you've got multiple load paths, that the old fail-safe thing, you've got other tyres there that are going to take the load. If we've got a burst tyre, it's not as critical as if it was a single or a double wheel. It says the wheels are smaller and easier to handle during maintenance. Yes, they are, but easier to handle, that's kind of debatable. Larger number of brake units. Yeah, we can put brakes in every wheel, so we're going to get much better braking. Disadvantages of the multi-wheel axles: more moving parts. Yeah, we need to carry out more maintenance. More complicated. So that's a disadvantage. And because of the size of the thing, the tyres tend to abrade, to scrub when they're turning. So we have to have a much larger turning circle so we don't get that scrubbing effect. Yeah, otherwise we just wear the tyres right down straight away. But obviously the advantages far outweighing the disadvantages. Ting, ting, ting. Yeah, there's about 14 pages of pictures coming up, just describing the different types of gear and the components that we're going to put on the landing gear. We'll look at the individual components later, but they're pretty much all of a muchness. We're going to have the trunnion, where we're going to attach the gear. For your large undercarriage, or for your retractable undercarriage, we're going to have some sort of retraction actuator. Yeah, we're going to have the side stays, or the drag stays. Again, we'll look at those. We need up locks, we need down locks. We need a method of attaching the bogie to the leg, and that's done via torque links. We'll have squat switches on the leg for our indications and for the various systems to work through. So yeah, different undercarriages. Yeah, but the layout might be different, but the components are, pardon me, going to be the same. Yeah. Oh, sorry, I thought somebody shouted at me there. Just let these guys in. That's done. Yeah, again, your main undercarriage leg, your main casting, the shock absorber that's built into into the leg, the torque tubes that hold the main leg to the bottom of the shock absorber. So we've got manoeuvring and steering. Brakes. We're going to put brakes on there, on the axle, and on the. Pardon me. We're going to have wheels on there. What's calling pintle up here is pretty much our trunnion. Retraction actuator that's going to pull the thing up and down, and again your drag steer, and you'll have a side steer. So much of a muchness. Your larger legs. So now we've got multiple wheels on. Again we've still got the drag struts, the side braces, and they're there to accept the different loads that the undercarriage is going to take during its operation. I'm pretty sure we'll come on to them later on, but the essentials of it is that as the undercarriage is rolling down the runway, it's going to be subject to different stresses. So we put the drag stay on and we put the side strut on to keep the wheels nice and level on the ground, and to accept those different loads. We don't want the gear folding up while it's in operation, so we put the struts on to accept those loads. Again, actuator for pulling the thing up into the body of the aeroplane. Some of your larger bogies have got steering on them, so we can actually steer the undercarriage unit. It's all tied into the nose wheel steering, but we might find on some bogies we've got the steering cylinders in there. Your axles on which your brakes and your wheels are going to go. The positioning actuator. Again, we'll have a quick look at that. Positioning actuator is there, so when the bogie is lowered, the wheels are going to tilt to the right position. The truck beam, as they call it, is just what's going to carry the wheels and the axles. Torque links to allow the thing to move. Brake equalising rods, we'll have a look at those. So let's see what we're saying in the notes there. Bogie undercarriage unit consists of a shock absorber strut, the lower end of which the bogie beam itself is pivoted. The axles attached at each end of the beam, so where we're going to put the wheels. Some aircraft, the rear wheels swivel on the bogie beam and caster when the nose wheels are turned through a large angle. On others, hydraulic actuators replace the torque link, and then nose wheel steering is applied. The whole bogie can rotate, which is quite handy. So if that's my bogie unit with multi wheels on, centre line of the aircraft, and we've got another. Just do them like that. As the aircraft is taxiing along and wants to turn, if we didn't have a huge turning radius, these wheels wouldn't have enough room to rotate as they were moving round, and because of that, the tyres scuff on the ground, and the rubber gets worn away very, very quickly. So what we can do is make the rear wheels on the bogie steerable. Put those little steering cylinders in. I say the rear wheels, that's generally where the steering occurs. No reason you couldn't do it on the front. But now, as the aircraft is manoeuvring, the bogie can steer as well, and it takes the pressure off the tyres and gives us that bit better steering as the aircraft is manoeuvring on the ground. What else have we got? During normal operations, the swivelling pairs of wheels are locked in line with the fixed pair. On the bogie as well, we'll put a bogie tilt jack, sometimes called the levelling strut. Yeah, and that is used to position the bogie beam at a suitable angle for retraction and landing. And that tilt jack acts as a damper when the aircraft first comes into contact with the ground. Yeah, so my little aeroplane. Yeah, as we lower the undercarriage, it's gonna tilt. I think it's the 777 tilts forward. But the idea is, as the aircraft hits the runway, yeah, rather than having the whole thing slamming into the runway, by gradually introducing it and allowing the rear wheels to touch first, it's making it a lot smoother landing, and it's taking away the stress from the aircraft and the shock of landing. Because don't forget, not only have we got a vertical descent, we've got forward motion as well, and that forward motion is going to try to push the gear backwards. Every action equal opposite reaction. Yeah. So by introducing it gradually, yeah, we can get this up to speed, and then the next wheel can come down, and then so on and so forth. And it's the tilt jack that positions the bogie. Also for retraction, yeah, it might be that we need to, as we take off, yeah, the wheels are still going to be in the inclined position. Might well need to bring them to the horizontal before we can retract the undercarriage up into the undercarriage bay. So that's your tilt jack. Yeah, to prevent the rear wheels lifting during landing or taxiing, we put brake compensating rods onto them. And all the brake compensating rod does is causes the brake torque to keep the back end of the bogie on the ground. Again, we'll have a look at that in a bit more detail in a minute. Whatever page it is we're on now, page 65. Yeah, the paragraph that starts, the bogie is designed so that the undercarriage provides two types of shock absorption. Yeah, the bit to highlight: when the weight is off the wheels, the bogie tilt jack ensures that the rear wheels are tilted down and touch first on landing. This jack prevents the front wheels of the bogie slamming onto the runway. Yeah, this jack is sometimes called a hop damper. Yeah, so highlight that bit so that we know what the tilt jack's doing, and we know that it's positioning the undercarriage so that it says the rear wheels in the notes, but certain aircraft it's the front wheels, but it's to prevent them slamming down into the runway, and that jack's sometimes referred to as a hop damper. The next paragraph down, yeah, again highlight the fact that the initial landing shocks are absorbed by the tilt jack, and the landing gear acts as a levered suspension. Yeah, once all the wheels are on the ground, the undercarriage becomes a direct action type. So what that's telling us, yeah, is that as the we've got the undercarriage unit, yeah, and the undercarriage unit is a shock absorber. Yeah, we're going to look at the shock absorption in a minute, and that is attached to the bogie. The hop damper, yeah, or the tilt jack, is making sure that the thing is positioned, tilted, ready for landing. Yeah, as we land, yeah, that tire is going to be the first thing to hit the ground. Yeah, and the shock of that tire hitting the ground is going to be absorbed by the tilt jack. So the tilt jack is acting as a damper for that initial contact. Then as the wheels are on the ground, the wheels will tilt down slowly, in a nice controlled manner, and then your direct shock absorption comes from your shock absorber. So now we're taxiing along, and the oleo is going to take the shocks. Does that make sense to everybody?
So
yes, Jim, no, Jim?
What are we going to write? Like, what are the two types of shock absorbing?
The bit that I've just said, we've got two types of shock absorber. Yeah, the initial landing shocks are taken by the tilt jack.
Okay.
Yeah. Then when the undercarriage is flat on the ground, the oleo shock absorber will then take the main shock absorber, as it calls it in the notes. That's going to absorb the rest of the landing loads. Okay with that? Don't forget, we're talking about a bogie undercarriage here.
Exactly, bogie. No, just. So these initial and oleo shock absorber are the two main type of shock load absorbed by the bogie type undercarriage, right?
Yeah, if that's your bogie, yeah, you're going to have a shock absorber. Yeah, the main oleo, the main shock absorber. Yeah, as the aircraft comes into land, that initial contact between the aircraft and the ground, that initial landing shock is going to be taken by the tilt jack.
Yeah.
Yeah, so I'll just draw a little beam there. That if you say that's the tilt jack, that is going to absorb the initial landing load. Yeah. Then the front of the undercarriage unit is going to load down to the ground gently. Yeah. So the whole idea of positioning it is so you don't get the whole undercarriage slamming down all together all at once. So once this touches down, the initial landing loads are taken by the tilt jack. Yeah, and your bogie lowers onto the runway. Yeah, and now your main shock absorber is going to take those landing loads. Okay. Happy with that?
Okay.
Doopy 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 doopy. See a picture of your tilt actuator. I was just looking through the notes there. There's about 400 pictures coming in now. Yeah. Steering cylinders, the undercarriage unit, and then we come to this where we've got the tilt actuator, the truck positioning actuator. That is going to, as we say, position ready for landing. And also when the aircraft takes off, the gear is going to be in the inclined position. It may well be that we need to bring it to the horizontal before we can retract it. And the tilt actuator will do that for us as well.
Hello, Jim.
Hello.
So, tilt actuator, is that truck positioning actuator. These are the same.
Yeah, it's the same thing. Yeah.
So when the aircraft is landing, the tilt actuator position the rear wheel so that it contacts the ground first.
Yes.
And when retracting, it also position the wheel so that it get retracted in the right position.
Yes.
Okay. Okay,
Yeah.
Jim.
That's
Thank
it
you.
exactly. Yeah. Can't say any more than that. Right. When we go on to page 72, it talks about the leveling cylinder snubber unit. Yeah. Rear end of the aft end of the truck moves down. Yeah, the unit's extended. When the aft end moves up, the unit's compressed. All that the snubber unit is there for is to make sure that the gear moves as it's going from the inclined position to the horizontal or vice versa. It's just making sure that it gets a smooth movement. Yeah, it's to prevent the truck pitching rapidly. If you can imagine, if we didn't have that, yeah, if we didn't damp the movement as we load the undercarriage down, the front wheel would drop rapidly, which is what we don't want. Yeah, so we need a nice smooth transition from the incline to the horizontal. So the leveling snubber unit is doing just that. It is a damper. Yeah, it's just a long convoluted name for a damper. So don't worry too much about that when you come across it. As it says, it goes on to talk about the internal workings of it. It's a damper. Yeah, all it's doing is slowing down the movement of the gear by passing fluid from one point to another. The text for it is a complete pain. It's difficult to get your head around using the drawings, so don't worry about it. The only thing that you need to know is that the snubber acts to prevent rapid truck pitching. Yeah, and that's about halfway. Was it 1, 2, third paragraph down? Yeah, that's. Stick your highlighter through that. That's all you need to know, that the snubber action acts to prevent rapid truck pitching, and it's just stopping the truck from moving up and down too rapidly. Everybody okay with that? Yeah. There is a picture of it in the notes, and trying to. I've got to be honest, try to work out what's going on inside the thing from the description of the text. It just takes far too long, and it's a pain to try and understand. So all we're going to try and say is that the snubber unit is there to prevent rapid pitching of the undercarriage. So your tilt jack's positioning the landing gear ready for landing, so that the rear wheels will contact first. The tilt jack will absorb those initial landing loads. The snubber unit, normally the snubber is within the tilt jack. It can be a separate component. But the idea is, as the rear wheels touch, you don't want these wheels slamming down quickly. Yeah, so the snubber is just going to act as a damper, and it's just going to lower the wheels onto the runway in a nice steady manner. That's the picture in the gear. Like I say, that's the damper mechanism. I don't propose to go into that because we don't need to, so long as we know what it's doing. Is everybody okay with that? Right, brake compensating rods then. What we do, they call them the equalising rods on here. They call them the compensating rods in the text. All that these are doing is making sure that the brakes are applying the same amount of force altogether all at the same time. If we didn't do that, a bit like if you were driving along in your car, yeah. As you're shooting forward in your car, racing car, because I know what you young lads are like. Yeah, as you're racing forward, racing around the streets of Kathmandu, and small child runs out in front of you. Yeah, you slam the brakes on, and what happens is the front of the car will tend to tip nose down. The back of the car will tend to tip nose forward as you're applying the brakes. If we tried to, if we allowed that to happen on the aircraft, yeah, the weight going on the nose of the aircraft could have a dramatic effect on the steering and everything then. So what we do to make sure that we get equal braking between the front and the rear wheels on the bogie, yeah, is we put a tie bar between them, the equalising rod. And the equalising rod is just there to make sure that the brake force is the same on the front wheel as it is on the rear wheel, and it stops that pitching action, stops the aircraft trying to pitch down as it's running forward while we're braking. Yeah, so again, page 74, yeah, the brake compensating rods arranged to produce a braking torque, so maintaining the weight force on the rear wheels of the bogie, and that produces more efficient and balanced braking. Yeah. Just a fixed rod, making sure that we get even force as we brake. Badoom. Yeah, that's a example of your equalizer rod. Yeah, just a big rod, and it's just there to make sure that we get the same brake force as we said before. Yeah, well, we've got it here. We've got our axles, we've got our main truck, the tilt truck, the main shock absorber, torque links. Yeah. The tilt positioning actuator will be up here somewhere. Maintenance of the thing. Yeah, maintenance of your bogie undercarriage. We saw that picture yesterday, yeah, and it's not an uncommon occurrence to find damage that severe on an undercarriage unit. If we've had a heavy landing, uneven landing, yeah, landed on one wheel, you can get severe damage. Yeah, so inspection when we're carrying out our maintenance of the undercarriage is really important. In addition to lubrication and testing and maintenance of the landing gear, particular care, high standards of workmanship required on bogie undercarriages. Because it's on heavy aircraft, yeah, high strength materials, but that's not to say that they're immune from damage. Yeah. Again, it says, you know, things like corrosion, scratching, indents, all lower the strength of the material. Yeah, so we've got to be careful. I'll come back to nose undercarriage in a minute. Just make sure that there's nothing on maintenance that we need to worry about. Yeah. yeah, just good husbandry, good trade practices. You know, things like fitting axle thread protectors, sleeves when we're changing the wheels. Carrying out all the procedures in accordance with the manual. That's all that little lot is saying. So nothing for us to worry about too much there. Anybody got any questions on bogie units? No. Lovely. Nose undercarriage then. Yeah, tends to get forgotten about in amongst all the other shenanigans, but obviously we need an undercarriage unit on the nose. And the nose undercarriage normally incorporates a shock absorber, the oleo shock absorber. Struts secured by trunnion and bearings at the top of the upper strut, again to a strengthened part of the fuselage. Nose undercarriage strut, normally a twin wheel unit with a fixed axle or a live axle. Remember we said the live axle was a turning one. Fuselage will have a area in which the nose undercarriage can retract into. Doors fitted so that the base closed when the gear's retracted. Normally on the nose undercarriage, the doors are mechanically linked to the leg. So when the leg comes up, the doors will automatically close that way. They're not a separate retraction item. Nose undercarriage retract forwards, backwards, or sideways. I've not seen one for eons, but there was aircraft that did have a sideways retracting nose undercarriage. I think it was the Trident, but I think that's a design concept that they've sort of gone away from. However, you never know; you might come across it. Nose undercarriage, we're going to have a steering system in there that can be operated from the cabin. And it says there may be provision for a nose wheel braking system. I have never in my life come across nose wheel braking. That's not to say it doesn't exist, but I personally have never ever come across it. Yeah. Again, you lads might. I don't know. So different examples of your nose undercarriage strut, yeah, shock absorber on it. The torque links are there to allow us to steer, yeah, and prevent us from going too far. This one we've just got the single wheel on the axle. Double one again. We've got the shock absorber. We've got the steering facility. We'll look at steering as a separate system later, and the twin wheels on the nose undercarriage. Components therein, yeah, torque links we've mentioned. The shock absorber mounted to the aircraft structure. We're going to have a drag brace, yeah, to take the fore and aft loads. Yeah. Retraction actuator. Not a lot else to stay there. Yeah. Mechanical linkages for the doors. So when the gear comes up, yeah, the doors will follow with the undercarriage mechanically linked, so they'll open and close. So what else do we need to say? Yeah, the components it's got on. Yeah, the undercarriage strut, the torque links. Torque links prevent the rotation of the lower strut within the upper strut. Lower torque link connected to the lower strut. Upper torque link connected to a collar mounted on the bottom of the upper one. Aircraft's on the ground. The torque links form part of the steering system. Upper torque link connected to the steering collar by a removable pin, which allows us to disconnect the steering system from while we're on the ground and we're moving the aircraft. Yeah. Ground locks, again, we'll look at the ground locks, but what we don't want to do is to have the possibility of the gear retracting on the ground. So what we do is we physical locks into the thing to prevent the actuators from retracting. Yeah, and with the nose undercarriage, we can put a pin through the retraction mechanism that does the job for us. So you got your ground lock. This one, steering actuators. As I say, we'll look at steering later. But normally on the undercarriage leg, there'll be a little plate, and that will tell you the range of steering available either side of neutral. Yeah, the normal level is 60-65 degrees, and then by disconnecting the steering, we can get an additional range of steering, so we can maneuver the aircraft on the ground. So if you're trying to put it in a tight corner in the hangar, or turn a tight corner outside as you're prepping the aircraft, and we can disconnect the nose wheel steering. We've got that additional range of movement for us. When the aircraft is taxiing, yeah, it can suffer what they call shimmy. And what shimmy is a rapid movement, fore and aft movement of the, side to side movement of the nose wheel. And obviously, if the nose wheel is going side to side, that is going to be magnified at the tail of the aircraft. And that is known as shimmy. Yeah. And shimmy is just this rapid side to side movement. Yeah. Causes the tail of the aircraft to be thrown rapidly from side to side internally. And it can be very, very uncomfortable. Shimmy, yeah. So you can imagine that's flapping about from side to side. That be going to be magnified. Yeah. Yeah. So to prevent shimmy, yeah, we normally fit 2 nose wheels, attach them side to side, yeah, or we can apply a shimmy damper to the aircraft. Yeah, so on page 78, I think it is, where it talks about shimmy damping. Yeah, nose wheel shimmy may be prevented on larger aircraft by using twin nose wheels, and shimmy damping provided by putting hydraulic pressure to both sides of a piston. This is your shimmy damper. All it is a piston with a hole in it. Yeah, so as the nose wheels are trying to move from side to side, the shimmy damper, as you can see, is the ram's being pulled or pushed backwards and forwards. So now the nose wheels can only go as quickly as fluid is passed from one side of the piston to the other, and that prevents the onset of shimmy. Yeah, prevents the thing from wobbling backwards and forwards. Anything else I need to say there? I don't think so. Yeah, your shimmy damper. Yeah, so now as the thing's trying to turn, yeah, we're just passing fluid from one side to the other, and that will damp out those oscillations. But the other favourite one is using twin nose wheels. Other thing we need, obviously when the aircraft's taken off, we need the nose wheels to go to the centre position. Yeah, we need them to centre. So what we do to give us that centering, if we've got nose wheel steering, we'll put a balanced actuator in that's going to bring the steering to a neutral position. But most aircraft incorporate a centering device in the nose oleo. And again, if we tried to retract the gear in that position, that's going to do an awful lot of damage to the structure. If we load the gear and the thing was in that position, it's going to make landing quite awkward, which is what happened to that particular aeroplane. So we'll put the self-centering device in. Self-centering device is just a pair of cams. Yeah, and when the aircraft takes off, when the oleo extends, yeah, the two cams ride together and lock the wheel in the center position. Yeah. So your cams, one fitted in the fixed cylinder, the other on the movable cylinder. During retraction of the nose gears, the weight's removed from the oleo. The oleo strut's extended, yeah, that drops down, and the sliding cam contacts into the fixed cam, and as it does, it slides it round into position. So your sliding tube, obviously, when the aircraft is airborne, that sliding tube has dropped. As it's dropped, it's caused the two cams to come together, and they engage, bring everything to the center position. When the aircraft lands, yeah, the sliding tube, the orange one, slides up the fixed tube, yeah, and disengages the two cams. Sorry, I thought I had a better picture of the cams in there. Sure, I've got one somewhere, but anyhow, I'll see if I can find it at tea break. Yeah, during retraction of the nose gear, the thing has got to self-center, and it does that by a self-centering mechanism within the leg. Lots of pictures, lots of pictures, lots of pictures. Ta-da. So now your shock absorbers, your oleo shock absorbers, yeah, these big beasts that are there to absorb the initial landing shock, yeah, and what they're trying to do is to prevent the aircraft from bouncing, from rebounding, yeah. We said that the initial landing shocks are taken by the tires. And the bogie tilt jack, yeah. If you haven't got a tilt jack, yeah, your initial landing, let's say the landing shock, not quite the right terminology, but that's going to be taken by the tire. Yeah, the tire will compress and it'll extend. Yeah, so there's a little bit of cushion in there. But then the weight of the aircraft comes down, and what we don't want to do is to allow the aircraft to bounce. So we're going to use a shock absorber there to absorb those landing shocks. Yeah, shocks transmitted through the wheel, runs on the axle, attached to the lower end of the undercarriage leg. Larger aircraft, the leg incorporates a telescopic mechanism which absorbs the landing gear shocks, but stops it from rebounding. Badoom, yeah. Your little fixed landing gear, yeah, fixed landing gear is just basically a spring, yeah, spring metal, and as the aircraft touches down, that sprung metal is going to absorb those loads. Yeah, sometimes. Yeah. Well, sometimes it all goes horribly wrong, but the idea is to absorb the loads. On your larger aircraft, we're going to have to use a more robust method, which becomes the oleo shock absorber. Components of our undercarriage, then. Yeah, we've said we've got the shock absorber. We've got the axle. The axle's got the wheel on it. The torque link connects the lower half of the cylinder to the upper half. So now any twisting load is going to be taken by the torque links. Don't forget, this is the main undercarriage we're talking about here. Yeah. So any twisting load taken by those torque links. The side strut is taking any side loads. Yeah, so as the aircraft touches down, the undercarriage would have a tendency to want to to move, so that the side brace, the side strut, is going to take those loads, and the drag brace, the rear strut, as it calls it there, I've always called it a drag brace. The drag brace is taking our fore and aft load. So remember, as we touch the ground, the wheels rotating. Yeah, there's a force coming forward, but there's also a force going back the way. And to absorb that, we're going to use the drag strut. I think that's a good time to stop and have a cup of tea, and then we'll have a look at how the shock absorbers work, and we'll highlight the bits that we need to there. Before we have a brew, then, has anybody got any questions at all from what we've done this morning? No? Okay, according to my thing, it's 10:12. I'll call it 10:15, so 10:35 my time. So that's 20 minutes, so it's about 22 minutes. So we'll go and have a cup of tea, stretch of the legs, and pat the dog or whatever. Okay?
Okay then.
All right, we'll see you in a few minutes then.
Okay. Mr. Jim,
Hello.
hello. You are having coffee?
Yeah. Well,
Let's
go
have
on.
coffee with some questions. What are the
News
two
off.
methods that ensure the nose landing gear is centered before it retract?
Yeah, what about it?
So one will be self-centered device,
Yeah,
and what about other?
that'll be the nose wheel steering. Yeah, we haven't covered steering yet, but the nose wheel steering, it's got a balanced actuator on it, and that'll always steer it to centre when the weight's off.
Okay.
Any more?
Mhm. And after retraction, like during retraction, is it oleo start?
During retraction?
Yeah, during retraction of the nose gear,
Yeah. What about it?
what bring it to the straight direction?
That's self-centering device. Yeah, that's centering device.
Mm-hmm.
I'll see if I can find a better picture in a minute. But this, what they call a plunger tube here, is fixed. Yeah. This sliding tube, the orange one, extends when the undercarriage is off the ground. So when the weight's on the nose, yeah, the orange bit is pushed up on the yellow bit, and it causes these two halves to disengage. When the aircraft takes off and the gear extends, that sliding tube, yeah, drops down, and it causes the two cams to come into contact with each other, and the little lock there, yeah, that little peg just makes sure that the two are locked together, and it's going to lock it in the central position.
Okay. Yeah.
Jim,
Yeah,
can you please show me the actual tilt jack? Where is it exactly in the picture?
the tail jack.
Tilt jack, yeah.
Tilt jack.
Tilt jack. Right.
Yeah.
Can you just give me 2 minutes? I'm just trying to find a picture.
Okay. Okay.
Mr. Jim,
Yeah.
I have got the picture. It is also called truck positioning actuator, right?
Possibly. I've not heard it called that before.
Yeah, because I have seen it. It is the tilt actuator, but sometimes it is called truck positioning actuator.
Oh, right, I thought you were talking about the centering mechanism.
Not tilt actuator, tilt jack.
Yeah, it's sometimes called the drop actuator.
This truck positioning actuator is in your slide, Jim. 2 or 3 slide before. The slide as well. Is the same tilt jack and the truck positioning actuator same?
What I think is it is same.
The tilt jack and the truck positioning actuator. Is that what you're talking about?
Yes.
This one.
Yeah. That is the same as the tilt jack. Yeah.
Yeah, exactly. Yes. That is the one which is also called tilt jack.
Okay, that's why I'm confused. Yeah. Who is the tilt jack?
Yeah, it's the same thing, just different names.
Same thing with a different name.
Yep, we find that a lot. Because you get the American terminology and you get the UK terminology.
So Jim, please let us know whether the synonyms same terminology, but
I did.
Yeah,
I promise I did when we talked about it. I said it's the same thing.
Because we are searching for a tilt jack in the picture, but couldn't find it.
Yeah, when I showed the picture, I said, "Oh, that's the same as the tilt jack."
Okay, Jim.
Yeah.
Thank you.
Obviously, I've done it a bit too quickly. I apologise.
Can you check your email, Jim? I have sent you the picture.
Thank you.
You got it?
I'll be there in just 2 ticks. That's something just coming through.
Jim.
Yeah.
This brake compensating rod, this causes the braking torque to depress the aft end of the wheel. That means it's release the brake on the aft wheel.
No. What happens if we didn't have that compensating rod when we were braking?
Yeah.
Yeah. The
aft wheel try to get off,
yeah,
right?
what would happen is the front wheel would be braking and the rear wheel would start to lift off the ground.
Okay.
So we put that compensating rod in to make sure that the brake force applied is the same at both wheels, and it stops that rear wheel from lifting.
Okay, okay, Jim. Got it.
Yeah.
Thank you.
Okay. All right, I'll be with you in 30 seconds. I'm just trying to. Here you go. Like that. All right, just for the centering mechanism, yeah, that is the lower leg, yeah, and it's held onto the top leg by the torque links. When the aircraft takes off, that lower portion's obviously going to extend, yeah, and as it extends, it causes the upper cam and the lower cam to come into contact with each other. Yeah, because those two have got the cam mechanism on them. Yeah, they're going to ride together, and they're going to make sure that the nose goes to a centered position. You with me? So now, when the aircraft lands, that upper cam is going to get pushed up with the strut. Yeah, so it's going to separate the upper and the lower portion.
Okay.
Just trying to find a picture with it compressed. But that is essentially what's happening for the steerer to the bringing it to the center position. Just lost my PowerPoint. Slideshow from current slide. Can everybody see the slide now? Okay.
Yes.
Excellent. Right. Yeah, that's just to show the leg. I thought that was already in this presentation, I must be honest. But just to reiterate what I was saying, we've got the lower piston, yeah, and that slides in the outer cylinder. There's two cams, one fixed to the piston end, the other fitted to the outer cylinder. So as the gear compresses, that upper locating cam is pushed away from the lower one. When the gear extends, they both ride together to steer the thing to the central position. Lovely cup of tea. You'd have lovely. That is nice picture. I'll use that. Thank you.
Welcome, sir.
Thank you very much. Right. So we're happy with the status centre. Yeah. So the shock absorbers then, yeah, to take the landing loads, we've talked about that. Where did I get to? Yeah, so your larger aircraft, we have the oleo shock strut, oleo pneumatic shock strut. Most fixed undercarriages, nose undercarriages, and most retractable undercarriages have the oleo shock absorber. Individual struts, yeah, depends on the type of aircraft, what type of strut we've got, but the principle remains the same. Yeah, the high loads placed on the undercarriage during taxiing, landing, ground handling. Yeah, so we're going to put braces on, and we've already seen those twisting loads taken by the torque links. Yeah, and then the main loads taken by the oleo shock absorber. They work on the same principle. Yeah, there are two types of shock absorber. Right, this is where you need your highlighter. Page 85, there are two types, with separator and without separator. Yeah, and we need to know the difference between them because it comes up quite often. Yeah, the one with the separator, yeah, what we've got is a sliding tube, yeah, and on the end of that tube is a piston head, yeah, and the piston head has got little drillings in it. Below the piston head, we have a separator, and below the separator is the area is filled with nitrogen, pressurized with nitrogen. The upper portion of the leg is filled with oil. And what we're going to use is the compressibility of nitrogen to absorb the landing load. So when the aircraft's airborne, yeah, the sliding tube is fully extended. The piston head is down at the bottom of the sliding tube. Yeah, the separator there separating the oil and the nitrogen. As the aircraft lands, yeah, the sliding part of the leg gets pushed up. As it gets pushed up, yeah, as the piston head goes up, oil is going to travel through the drillings in the piston head. And this little creature here, the flutter plate, yeah, is très important. Yeah. As the oil's flowing through, it pushes down on that flutter plate and it gives the oil a free passage, or a relatively free passage, into the lower half of the chamber. At the same time, the oil that's coming through is compressing the nitrogen. So the nitrogen's getting squeezed and squeezed and squeezed until it gets to a point where it says, sod that, I'm not having any more. And it tries to extend, it starts to extend. So that pressure on the nitrogen then is pushing up on the separator. As it's pushing up on the separator, obviously it's pushing up on the bottom half of the leg. Leg's trying to come back down. Yeah. So what's happening? The oil is being forced back through the drillings in the head of the piston. But because the oil's going that way now, it closes off the flutter plate, that and spring pressure. So the oil pressure, spring pressure closes the flutter plate. So some of the drillings are closed off. So now the passage of the oil is restricted. Yeah. So relatively free coming this way as the leg's compressing. Now as it's trying to extend, yeah, it's being restricted. So the leg can only extend as quickly as the oil can get through the drillings in the head. So it's not going to bounce, yeah, it's going to gradually extend, yeah, and so it's absorbed the landing shock. Yeah, so the one with the separator, yeah, outer cylinder slides a plunger tube or a lower cylinder, prevented from rotating by the torque links, we've mentioned that. Lower cylinder piston head contains a spring-loaded flutter plate. Yeah, right, yeah, stick your highlighter through the words flutter plate. Yeah, it's the flutter plate and the separator that identify this particular type of shock absorber. So if it's got the separator in, it's got the flutter plate. Absorber charged with oil and compressed nitrogen. It says air, but nitrogen's what we use. The separator in the lower cylinder separates the oil from the gas. Top of the outer cylinder is closed. Two oil filler plugs up there. Needn't worry about that just at the minute. Aircraft's airborne. Gas pressure moves the separator up the lower cylinder, forcing the oil into the outer cylinder. That fully extends the leg. The aircraft lands. Yeah, its weight telescopes the oleo leg, and the oil in the outer cylinder lifts the flutter plate and passes freely into the lower cylinder. Oil forces the separator down, compresses the gas, and in doing so, it's absorbing that landing shock. At the end of the compressing stroke, yeah, the compressed gas expands, forcing the separator plate up and consequently the oil to flow back into the outer cylinder. Sorry, I'm just itchy eye. Yeah, the spring closes the flutter plate and the flow of oil is restricted to the it says 2 holes in the piston. In reality, there's probably more than that, but we'll call it 2 because of the diagram. So the flow of oil is restricted to the 2 holes of the piston. So the speed of the extension of the lower cylinder is limited to the speed at which the oil can flow through. And that slows down the rate of extension and damps out any tendency for rebounding. When the aircraft's stationary, the leg's slightly compressed until the resultant force causing the extensions equal to the weight of the aircraft acting on it. Don't worry about that bit, but it's the fact that we've got the separator, and if we've got the separator, we've got the flutter plate. Yeah. Flutter plate sits on top of the separator sits on top of the nitrogen. Aircraft lands, yeah, and as the leg compresses, the oil's passed from the top half of the cylinder through the drillings in the piston head into the lower half. At the same time, it's compressing the nitrogen. Yeah, we'll get to a certain point where the nitrogen will start to expand. Yeah, as the nitrogen's starting to expand, yeah, we're now passing oil from the lower half of the cylinder into the top half. But because the flutter plate is closed off, the passage of that oil is very much restricted. So we've absorbed the shock of the landing, and now the extension of the leg is being regulated by it can only move as quickly as the oil can pass through that piston head. Everybody okay with that? That's the with separator. If we've got the with separator, we've got the flutter plate in there. Okay. Yeah. Really, the bit that we need to highlight is the fact that the separator and the flutter plate are in the same leg. It doesn't quite mention them in the same paragraph. So whichever was easiest for you to highlight the fact that the with separator shock absorber has the flutter plate. Yeah, and again, just yeah.
That means we can say that the landing shock is taken by compression of gas. Huh?
Yeah.
Okay.
Yeah, so it's the oil passing through the cylinder, compressing that nitrogen, that's absorbing that landing shock, and then what we don't want is the aircraft bouncing along the runway. So by restricting the passage of oil now, yeah, we're preventing that rebound.
Okay, that means rebouncing is controlled by the controlled flow of hydraulic oil from the orifice.
Through the orifice, yeah, from the bottom half to the top half. As the thing's compressing, it's got four, in this case, 4 holes for the oil to pass through, so it can pass relatively freely.
High flow rate,
Yep.
yeah.
On the way back up, yeah, the flutter plate closes. Yeah, spring pressure will close the flutter plate, so now it's only got 2 holes to flow through. So you've got a restricted passage of oil, so it can't extend as quickly.
Too quickly. Yeah. Okay, Jim. Thank you.
Yeah, my pleasure.
Jim.
Anybody else?
Jim,
Yeah.
Is it the smooth movement of the oleo is during rebound is due to the oil passing through this drill area, or due to the piston that causes close during the extension? Because restriction is from the piston, right?
Yeah, if you imagine that's your shock absorber that you see on the aircraft, yeah, you've got your nitrogen area, yeah, and then you've got your separator, yeah, and as the aircraft lands, this inner inner cylinder is going to move up in the outer cylinder, yeah, and then you've got your piston head up here with the holes in. So it's the as the when the leg's airborne, yeah, the inner cylinder is dropped right down, if you like, through gravity. Yeah, so all the oil is in the top half of the leg. Yeah, and there's no pressure the only pressure on the nitrogen is what we've put in there initially. The separator is keeping the oil and the nitrogen apart. As the aircraft lands, that leg compresses. Yeah, so you got your wheel here. We've hit the ground. The inner tube, if you like, is pushed up into the outer cylinder. As it gets pushed up, obviously all the oil is getting squeezed, so it's going to run through these tappings in the piston head, and it's going to fill the bottom half of the outer cylinder. At the same time as the oil's coming through, it's opening the flutter plate, yeah, allowing more oil to flow through. So the leg is going to get to the point where the oil has passed through and it's all gone into the lower half of the outer cylinder. At the same time as that oil's passing through, it's compressing the nitrogen. It's pressing down on that separator, and it's compressing the nitrogen. And the leg's designed so that when the nitrogen gets to a certain pressure, yeah, it'll start to fight back. It'll start to expand again. And as that nitrogen starts expanding, yeah, it's pushing up on that separator plate, which is causing the oil to flow back through the piston head into the top area. But because of the spring, that flutter plate closes. So now as the leg is trying to extend, yeah, because we've compressed. Now the leg's trying to extend. Yeah, the oil can only go through or the leg can only extend as quickly as that oil can go through those drillings. And because the flutter plate is closed, we've lost 50% of those passages. So now the leg can only extend as quickly as the oil can pass from the bottom half to the top half. And that's what stops the aircraft from bouncing, from rebounding. Yeah?
Excuse me, sir. Jim,
Yeah.
I have one question. I have option also. I am bit confused about this. Can you answer me, please? In oleopneumatic shock absorber, if the fluid level is low, then option is flutter plate will not close and the rebound damping will be too fast. Second option is gas will have expanded and cause the fluid to transfer through the piston head too slowly. Third option, speed of the shock absorber when it extends will increase and reduce the damping of the rebound.
Well, let's go through that and you answer the question.
Okay, sir.
Okay, so what was the question?
In oleopneumatic shock absorber, if the fluid level is low, then what will happen?
Okay,
while landing.
If the fluid level's low.
Yes.
Yeah. So what's going to happen then?
Yes.
So what was the first option?
Flutter plate will not close and rebound damping will be too fast.
Well, will the flutter plate close? Yeah. If you've got a low oil level, will it
yes.
close? Should do, shouldn't it?
It will not close, sir.
Why wouldn't it close?
Because of compression is there, no?
It's got a spring on it.
Yes.
Yeah.
Yeah.
What was the second option?
Second option, gas will have expanded and will not cause the fluid to transfer through the piston head too slowly.
No, because your nitrogen's fine, isn't it? The nitrogen's going to push the oil.
Second option is not there. It's not good. I think second option is not answer.
So what was the third one?
Third one is speed of the shock absorber when it extends will increase and reduce the damping of the rebound. I think third option is good, sir.
Yeah. See? So you did work it out.
Yeah.
Everybody else okay? Yeah. With separator. If we've got the separator, we've got the flutter plate. Yeah. And again, just showing the separator, the gas, the nitrogen in the lower half of the leg. It's not a fantastic drawing. You can see the oil in the top half of the leg. As the leg compresses, yeah, the nitrogen compresses, yeah, and what it's trying to do is to push the oils come through, yeah, and as the leg tries to extend now, pushing through, and the flutter plate is going to reduce the flow of the oil, so we're damping out that rebound tendency. The other type of oleo we get is without separator. Yeah, the without separator one works on the same principle, but it doesn't use a separator to keep the oil separate from the gas. Yeah, the pressures in it are carefully worked out. So that the gas isn't absorbed by the oil. Yeah, but it works on the same principle. What we're doing is slowing down the passage of oil through a restricted portion. Yeah. And what we use to achieve that is a metering pin. Yeah, the metering pin is tapered. And the metering pin goes through an orifice in what they call a piston support. Yeah. So we've got the inner cylinder. Yeah. We've got the outer cylinder, and fixed to the outer cylinder is the piston support. On top of the oil is our nitrogen. Yeah. And then the dark blue is our oil. Yeah. As the leg collapses or compresses, I should say. In fact, what I'll do, doesn't use a separator. The outer cylinder fixed rigidly to the airframe structure by two mounting brackets. Inner cylinder and a piston assembly, the inner space being partially filled with oil and inflated with nitrogen. Inner cylinder is free to rotate and move up and down, but the rotation limited by the torque links. We know all that. We've had a look at that. Under static conditions, the weight of the aircraft is balanced by the struck gas pressure in the inner cylinder, and it takes up a position approximately midway up its stroke. Yeah, so the aircraft weight is balanced. Under compression, yeah, so when we're landing, the strut shortens and fluid is forced through the gap between the piston orifice and the metering rod. So as the leg compresses, yeah, the oil is forced up through that gap between the fixed piston support and the metering pin. Don't forget that metering pin's tapered. Yeah, as the internal volumes of the cylinders decrease, the gas pressure rises till it balances the upward force. Upward force decreases, the gas pressure extends, acts as a spring, extends the inner cylinder, but the extension can only happen as quickly as the fluid can flow through the orifice. Yeah, so the aircraft, the leg extended, oil, gas, aircraft lands. Yeah, the leg compresses, that metering pin, yeah, is pushed up through the orifice. As we push up, yeah, that gas is compressed. It'll get to a certain point. Once the landing is completed, the gas will reach a certain pressure, then it will start to expand again. And as the gas is expanding, it's pushing the oil back through into the lower half of the cylinder. But that oil can only flow, I say only flow, as quickly as the metering pin will let it. Because the metering pin's tapered, yeah, there's going to be a gradual flow of oil. Then there's the leg slowly extends, little bit more, little bit more, little bit more. So again, we've damped out that rebound tendency. So we've absorbed the shock of the landing, yeah, and then by restricting the passage of oil back through, yeah, we've damped out the rebound tendency, and that is the metering pin type. So with the metering pin type, we do not have a separator. The gas sits on top of the oil. With the separator type, we have the flutter plate. Please don't confuse them. Highlight it whichever way you want to, but they are two separate types of shock absorber. The principle's the same, but the method of operation is slightly different. All okay with that?
Jim, this metering pin type.
The metering pin type, yeah. Yeah, again, just same sort of thing. Yeah, just showing you've got your metering pin, you've got your oil, you've got your gas, your support tube. Yeah, so as the leg compresses, yeah, the fluid acting on the gas compresses the gas. Fluid passes through, but as the metering pin goes through, it's reducing the area between the support and the metering pin. So now as the gas pushes down on the oil trying to extend the leg, the oil can only pass through, yeah, as quickly as the distance between the metering pin and the outer wall will let it. Yeah, so pushing down the piston, that oil flow is going to be restricted. Everybody okay with that?
I couldn't understand. Could you please repeat it one more time?
Well, the metering pin one.
Yeah.
Right. This outer cylinder, in fact, might be a bit clearer on this one. This outer cylinder is the undercarriage leg, yeah, and that is fixed to the airframe structure. Inside it, where we attach the wheels, yeah, we've got a sliding piston, and this sliding piston will move in and out in the outer cylinder. Okay with that so far?
Yeah, got to this point.
Right. This support mechanism is fixed to the leg, so this thing is fixed. This isn't gonna move, but the inner portion of the leg will. So what we do is we fill it partially with oil, and on top of the oil we're going to put nitrogen, yeah, and we're going to charge that nitrogen to a base pressure. As the aircraft comes into land, yeah, the leg is going to compress. Yeah, so this inner sleeve, pushing on the piston, is going to compress. Yeah, and that metering pin is going to get pushed up through this hole here. All right, so we've got a hole. That's that tube thing that we're looking at. The metering pin is tapered. Yeah. So the further that pin moves up, the smaller this gap is going to be. Do you see what I mean? So as the metering pin moves up, it's reducing the distance between the pin and the outer cylinder. That gap gets smaller. Yeah?
Okay.
Right. Now the leg wants to extend. Yeah. So what's going to happen as the leg's trying to extend? Yeah, the oil is trying to move from one side to the other. Yeah. So as that pushes up, pushes the oil through that way, squeezes the gas. The gas pushes down, yeah, which is going to push down on the piston. So now the oil has to move from one half of the chamber into the other, but the oil can only go as quickly as that gap will allow. So now, as the leg's trying to extend, yeah, the oil is being restricted in its passage through. Yeah, it can only travel as quickly as that metering pin will. So now, as the leg's extending, it's only going to do so slowly, which has damped out the tendency of the oleo to bounce. Yeah, as the leg extends slowly, obviously that metering pin is starting to withdraw, so that the gap starts to increase. Yes, the longer it goes on, the more the oil can flow. You with me there?
Yeah.
Yeah, and that's all it is. It's the same principle. We're just restricting the passage of oil to slow down the extension of the leg on the rebound stroke. So as it compresses, it'll absorb those landing shocks. Yeah, as it tries to extend, it's only going to do so slowly, so it's stopping the leg from rebounding.
Okay, Jim. Thank you.
Are you sure?
Yeah, I got it.
Pinky promise?
Pinky promise.
Excellent. All right, detail X. Yeah, forgot about that.
Excuse me, Jim. Excuse me.
Yeah.
The orifice support tube in the picture,
Yeah.
it has also orifice in its body. The picture is showing like that. Orifice support tube. Yeah.
That one. Yeah.
Yeah. That is also orifice.
This is what they call the orifice, where the metering
Yes.
tube goes through.
But in orifice support tube, there is also, we can like see, it is not continuous, you know.
Oh, yeah. There's little perforations in it. Yeah.
Okay.
Yeah.
Okay. Thank you, Jim.
Right. When it talks about dimension X, we need to make sure that the leg is filled properly. Yeah. That we've got sufficient oil in it and we've got sufficient gas pressure in it. The procedure for filling and charging the legs is written down there. I'm not going to go through that. Filling and charging the legs, we don't really need to worry about that. Remember, depends on the type of shock absorber you've got, how we're going to service it, but we're always going to service it in accordance with the AMM. Yeah. Where are we? Your large undercarriage shock absorber. Yeah, the Oleo shock absorber is made from steel. Inner cylinder, outer cylinder, orifice support tube, metering pin. Support tube attached to the top of the outer cylinder. Upper and lower bearings provide sliding surfaces. Don't need to worry about that. Between the lower bearing and the spacer, a seal adapter with annular grooves. Don't need to worry about that. Sometimes shock struts have little grooves in the lower bearing for storage of spare seals. So your spare seals, we can replace damaged ones without having to completely disassemble the shock strut. Shock struts filled with hydraulic fluid in the compressed position. The fluid fills the space between the inner and the outer cylinders. Strut then inflated with nitrogen to the specified pressure. Weight of the aircraft balanced. Yeah. On landing, the Oleo strut compresses. The fluid forced through the gap between the orifice and the metering pin. That restriction limits the speed of compression of the Oleo. As the internal volume of the cylinders decreases, the gas pressure rises. Upward force decreases, gas pressure acts as a spring, extends the strut. Speed of the extension is limited by the flow of the fluid through the orifice. Some Oleos, fluid in the annular space between the inner and the outer cylinder is forced through a restrictor. Some of them, there's a gap down there between the two pistons, or between the two cylinders. Not all shock absorbers, but some, they have a gap down here that fills with oil as well, and there's a little non-return valve in. Not non-return valve, a restrictor. We needn't worry about that too much. We're just worried that the fact that it's the oil passing through the orifice, and the orifice restricted by the metering pin is what's slowing down the extension. Yeah, because we're going through that restriction. Yeah, that prevents violent extension of the Oleo, and obviously damps out the bouncing tendency. Happy days. Right, dimension X that we were talking about. When you look at an undercarriage leg, pardon me, you see a shiny bit at the bottom. That's known as the fescalized portion. Yeah. And that fescalized portion is what we refer to as dimension X. Yeah, so we can use dimension X to check that the Oleo has got the right extension for the amount of pressure that's in it. Yeah. What we do to check, yeah, that's dimension X, the shiny part. Yeah, stick a gauge on the charging valve. Whatever it is. Some aircraft, there's actually a gauge already fitted if you're lucky, and it'll tell you what pressure's in the leg. We go to a chart in the AMM, and that chart will tell us what dimension X is and what pressure should be in the leg. Yeah, so if I go to dimension X on my aeroplane and I measure dimension X at 19 inches, yeah, it should have around about 1,000 psi in it, somewhere between 950 and 1,000 psi. If I've got that reading on the gauge, I'm happy. If I'm out with that, yeah, I need to recharge the leg. Yeah, it does give you the fully compressed strut, the fully extended strut, yeah, and the pressure that's in there. So you can check dimension X if your aircraft's up on jacks. Normally, it's a job to do it when the weight of the aircraft's on the ground. But all we do is trot off, yeah, measure dimension X, have a look to see what pressure should be corresponding to the dimension we've got. Alternatively, you could have a look at the pressure gauge and say, oh, yeah, I've got 1,600 psi in there. Yeah, what should my extension be? Extension should be 13 inches. And again, if the two don't marry up, then we need to either adjust the pressure in the leg, top it up, or reduce it. So that's our dimension X. Yeah, so we check it against the servicing graph. Ching, ching, ching. Some nice pictures. Picture of the graph. Anybody got any questions, queries there? Yeah. With separator, flutter plate. Without separator, metering pin. And then we have the liquid spring shock absorber. The liquid spring, we've always said that fluid is incompressible. Yeah, but the liquid spring uses a special oil, a synthetic silicon-based fluid that actually will compress. Yeah, the liquid spring filled with oil, and because it's compressibility, yeah, it'll have the same sort of effect as the standard shock absorber. Yeah, aircraft's airborne, shock absorber fully extended. Valve in the piston head, little valve there, is in the closed position. Aircraft lands, yeah, the weight pushes the shock absorber, the piston rod's forced up into the cylinder, compressing the oil, and that valve in the piston head's going to open. So as the piston goes up, the oil is going to open that valve and it's going to flow into the bottom half of the chamber. Once we get to the certain point, yeah, pressure equal on both sides. It says because the area on the top surface is greater than the area on the bottom surface. Once we reach the end of the stroke, that compressed oil is going to start pushing down on the piston. Yeah, greater force above the piston head tends to eject the piston rod at high speed. So the oil's pushing down. As it's pushing down, the oil in the lower half of the chamber is allowed to move up through a little orifice. But because the piston head's coming, try to extend, yeah, the valve's closed. So it slows down the movement, yeah. Greater force above the piston head ejects the piston rod at high speed. With this extending movement, the valve in the piston head closes. So the flow of fluid from below to above is now restricted through that small drilling. And again, that slows the speed of the rebound. Okay with that? So we land, yeah, piston goes up, oil forced through, opens the valve, and the oil can flow through in the bottom half. As the piston tries to extend now, yeah, coming down the way, the oil in the bottom half is restricted to just going through that little orifice. Yeah, the valve's closed, pushed up by a spring. So now the extension is regulated, restricted. So we damp out that rebound tendency. Right, the bit on the bottom of page 98 where it talks about piston rod sealing. Yeah, the gland assembly, which is all this lot down here. Yeah, we've got the retaining nut, we've got a backing plate, we've got a gland ring and a pressure plate. Yeah, the gland assembly prevents leakage of the cylinder, whereas the cylinder pressure, whatever the cylinder pressure is, by application of the principle of differential areas. And then it goes through to explain it. Basically, it's because you've got these two pins in here that creates a differential area. So whichever way the thing's operating, this gland is always going to seal. Again, I don't particularly want to waste hours going through that. Have a read through it. If you want me to go through it later on, I will. But we don't need to. All we need to know is that sentence there: the gland assembly prevents leakage of the cylinder contents, whatever the cylinder pressure, by the application of the principle of differential areas. Yeah. Boom, and that's what it's about, because you've got these dowel pins, yeah, going through the gland ring. Whatever pressure's acting on there, the pressure acting that way, compressing it, and it compresses that seal, and then the pressure going the other way has the same effect. As I say, I don't really want to go bouncing into it, but have a read through. But all you need to know, and stick your highlighter through it at the top there of the page 98, under piston rod sealing, that first sentence: the gland assembly prevents leakage of the cylinder, whatever the cylinder pressure, by the application of the principle of differential area. Okay. Anybody got any questions there? Fantastic. Where we're going to get the liquid spring? Yeah. Things like the articulated levered suspension. Because the liquid spring, because the action of it can be built a lot smaller. Yeah. So whereas a direct action shock absorber has got to be fairly large, the liquid spring will fit into a smaller place. So it's quite handy. They do exist. They're still in use in places, but you don't see them all that often now. Yeah, but that's the idea of it. The liquid spring, yeah, just gets us into smaller areas. The articulated levered suspension, yeah. Oleo strut can be compressed by direct action or articulation. Direct action method has the disadvantage of requiring a large, strong strut. Yeah, but it's got to resist the side and the drag loads as well. The articulated or the levered suspension allows us to use a small shock absorber, small strut. Yeah. Levered suspension method more efficient, as the oleo is of short length and operating stroke. So the possibility of the strut bending or jamming or anything is remote. Another advantage is that the renewal of a levered suspension oleo is simple and less difficult. Yeah, and as it says there, the small liquid spring shock absorber suitable for levered suspension undercarriages. Right, that was our shock absorbers. Has anybody got any questions, problems with those? Right, what we'll do, we'll just have 5 minutes there. 11:27, 11:30, 25 to. You can have 8 minutes, and then we'll look at breaks, and that'll take us nicely up to lunchtime. If nobody's got any questions, we'll just have that 5-minute break, and I'll see you in a second. Let you stretch your legs. Right, everybody back? Looking good. Right. If nobody's got any questions, then we will rattle on with brakes. That's the next part of our undercarriage system. Powered brakes. Yeah. So we need brakes. Yeah, most modern transport aircraft fitted with twin nose wheels, twin wheels, or bogie. Yeah, brakes normally fitted in the main wheels. As I say, I've never come across nose wheel braking on any aeroplane, but that's not to say it doesn't exist. Top of page 102. Yeah, the brakes, the brakes to convert kinetic energy into heat. They're going to slow us down, yeah? So by slowing us down, they're providing drag, yeah? And those brakes, as well as converting the energy to heat, providing that drag, they've got to disperse that heat as well. So we need to get rid of that heat. Boom, yeah. So the brakes, depending on the size of the aircraft, each main wheel is going to have its own brake unit there. Just to run through the bits on there, we've got rotors, and those little rotors engage with the drive blocks on the wheel that we saw yesterday. They engage with the wheel. The wheel carries the rotors round, and attached to the rest of the brake unit we have, and ergo the axle, we have stators. When we apply the brakes, there's hydraulic pistons push the rotors and the stators together, and as the rotors and stators are in contact with each other, they provide that retarding force. They're going to slow the aeroplane down. What we're not going to do is just jam the brakes on, yeah, and bring the aircraft to a skidding halt. It's got to be a nice gradual process, yeah. So your multi-disc brakes provide friction surfaces for your braking. Yeah. We can have single disc, we can have multi-disc plates. The one we're looking at here, multi-discs. Yeah. So we have the torque plate, and the torque plate contains all the gubbins. Yeah. The cylinders operated equally around the torque plate. Friction elements in the form of pads attached to either side of the stationary discs. Yeah, so we've got our torque plate, a pressure plate, and then we've got the rotors and the stators. The rotors, just discs that are carried around with the wheel. The stators, little pads, and as we apply the hydraulics, the lot are squeezed together, acting against a thrust plate. Yeah, and that gives us our retarding force. Friction elements in the form of pads. Yeah, some types, the rotating discs have sintered surfaces or pads, which it's just an impregnation in the material which allows for better heat dissipation. Carbon brakes, the rotors and the stators are made from carbon. And we'll go into operation in just a minute. Yeah, multi-disc brake. Yeah, torque plate, torque tube assembly fits over the axle. So your torque plate and your torque tube. Yeah, that fits over the axle of the aeroplane. Yeah, bolted onto a flange on the axle. Number of cylinders spaced around the torque plate, connected to the hydraulics. And those cylinders have got pistons in which apply the load to the pressure plate. Your pressure plates are disc pack. The disc pack is referred to as the heat pack, and that contains alternating stationary and rotating discs. Stationary discs keyed to the torque tube, rotating discs driven by the wheel. We've said that. Correct working clearance in the disc pack maintained by means of adjuster assemblies. Pins attached to the pressure plate protruding through indicate the amount of wear that the brake unit has got. Yeah, don't think it shows it on this one. We'll come to wear in a bit, but obviously where we've got friction, we're going to get wear. So eventually these pads and rotors are going to wear down. We'll get to a point where we need to replace them, and we can tell how worn they are by the amount of pin that's protruding through. So we'll get to that in a minute. Torque plate held onto the slides over the axle, and it's bolted onto the axle, secured to the axle. The stators held onto the torque plate by little drive blocks, and they remain stationary with the torque plate. The rotors driven around by the wheel. Ta-da! Most modern brakes, it says, is the carbon brake. Discs of pure carbon made from carbon fibres bonded together by another carbon substance. Yeah. Carbon can absorb more than twice the amount of heat absorbed by steel for the same rise in temperature. So it's a very, very good heat sink, and it saves a lot of weight. Yeah, so carbon brakes, again, I can't remember whether, I think that was a mock question, but just stick your highlighter through that bit about carbon brakes on page 104. Yeah, carbon can absorb more than twice the amount of heat absorbed by steel for the same rise in temperature. So used as a heat sink, it can save an awful lot of weight. Transfer of heat from the brake to the wheel and the tyre minimised by fitting heat shields or putting cooling fans in the wheel. But in the wheel as well, we've got those vents that we saw yesterday that allow the wind rushing past to take the heat away. Yeah, brakes operated from the pedals, the rudder pedals, and the cockpit. But instead of pressing the rudders left and right, what we're doing is pressing the top of the foot pedals, and that applies pressure to the brakes. Yeah, pistons move, press against the pressure plate, disc packs clamped between the pressure and the thrust plates, squeeze together like the filling in a sandwich, and those friction loads slows down. Yeah, brakes are released, springs in the adjusters move the pressure plate back to maintain a working clearance. When we talk about a working clearance, what we don't want to do is have too much movement in the brakes. Yeah, so from pressing the pedal to the brakes applying, it needs to be fairly instant. Yeah, and as the brakes wear, we need to maintain that clearance. Yeah, and we do that by means of adjusters. We'll look at how they work later on, but when it talks about the working clearance, yeah, they've got to be free to rotate when the wheels are rotating, but they've got to be close enough to apply when we press on the pedals. Anything else we need to worry about there? I don't think so. Yeah, carbon brake. Yeah, your rotor, your stator. Not a fantastic picture there. The pin that sticks out is the wear indicator pin. So the more the brakes wear, the less protrusion you get on that pin. When it gets to a certain point with the brakes applied, a certain measurement, then we need to replace the heat pack. That we can do rather than replacing the whole brake unit. Yeah, most times we can just change the heat pack, the rotors and the stators, and that saves an awful lot of work as well. Anything else? That's just the pressure plate with a pin protruding through. Our wear indicator. So we just have a look at that. Can't see much else. No. Top plate bolted onto the axle. Yeah, piston housings equally spaced. In this one, we've got the brake rod attachment point. Yeah. pressure plate, thrust plate at the back, squeeze them all together, and away we go. Maintenance of the brakes, yeah, just looking for contamination, no leakage on there. Obviously, because they get hot, we don't want any oil dripping onto them. You get the subsequent fire and what have you. Checking for wear, we've already mentioned that. Nothing else we need to worry about there. Nothing we need to worry about there. No, just there's just a big load of stuff on 108 telling us what we should look for. Nothing that we need to concern ourselves with. Yeah, no, that's all fine. Right, just out of on that maintenance thing. I think it says there somewhere in the screed, but if you do get involved with carbon brakes, be very careful, because the carbon brake will generate an awful lot of dust. Yeah, and if you breathe that dust in, it can do quite a significant damage to your lungs. So if you're working on and around carbon brakes, I would strongly advise you put some sort of face mask on to protect you against carbon dust and COVID. The adjusters, as we said, the adjusters are there to ensure that the brakes maintain a suitable running clearance. Yeah, multi-disc brakes, they're attached to the pressure plate. Yeah, and what have we got? Yeah. A multi-disc brake normally attached to the pressure plate. An operation, movement of the piston or the pressure plate transmitted via the retraction pin and friction bush to compress the adjuster spring. Move the guide till it butts the torque plate. Yeah. What have we got then? We've got our torque plate, and screwed onto the torque plate is our adjuster assembly. Running through the adjuster, inside the adjuster, we've got a guide, yeah, and that guide holds what they call a friction bush. The friction bush allows movement one way through it only. Yeah. Behind the guide is a spring. Yeah. The pressure plate is what keeps the brakes next to the heat pack. Yeah. So in operation, the movement of the piston of the pressure plate is transmitted via the retraction pin and the friction bush to compress the adjuster spring. So as the pressure plate moves, yeah, that pin is pulled through the friction plate, and as it's pulled through, that guide and the spring compress. Yeah. When I release the brakes, yeah, the spring will extend, and via the pin, it'll pull the pressure plate away from the pulls the guide back until it contacts the spring housing. Clearance between the guide and the torque plate is the designated running clearance. So as we apply the brakes, we want that clearance between the what am I saying? The pressure plate and the brake unit. So as I apply the brakes, pressure plate's gonna get pushed against the rotors and stators. It's going to pull on that pin, and at the same time, as it moves, it's pulling down on this guide. That compresses the spring. When I release the brakes, yeah, the spring is going to push the guide back up to the far end, and in so doing, as the spring pushes up, it's pulling the pressure plate away from the brake unit, or the heat pack, I should say. Sorry. So every time I apply the brakes, that pressure plate is going to move slightly. Yeah, as it does, as it moves, it's compressing this spring. The spring compressing with the guide pressing down on it. Release the brakes, the spring presses back, and as it pushes back on this guide, because this bush is one way only, it's pulling the pin and pulling the pressure plate away from the brakes. So we're always going to maintain what they call the running clearance when the brakes are off. Because this bush is one way only, yeah, we can use the pin as a wear indicator as well. Yeah. Does that kind of make sense to everybody? Yeah.
So
Lovely.
this Jim, retraction pin is same as this wear indicator.
It will double up as a wear indicator, yeah. But that pin, yeah, is hooked onto the pressure plate. Yeah, so every time I apply the brakes, the piston is going to push the pressure plate against the brakes. Yeah. So if you can imagine shouldn't do it in red, but you've got your heat pack here. Yeah. That's your rotors and your stators and all the rest of it, and then you've got your thrust plate at the back. So every time I apply the brakes, there's going to be a piston presses the pressure plate against here. As it does, it pulls that pin through the bush. Yeah, and the movement of the pressure plate as it pulls the pin through the bush, it's compressing this spring with the housing bit. When I release the brake pressure, that spring pushes back on the housing, and it pulls the pressure plate away from the heat pack. So every time I release the brake, there's going to be a gap here. Yeah, and that gap is going to be the same as that gap. It's not going to be very much at all. But this friction bush is a one-way bush only. So it'll allow the pin to go that way, but it won't allow it to go the other way. So as the spring pushes back on the guide, this pin will stay in its original position within the bush. Yeah. So now as the brakes start wearing, yeah, we can start to look at how much pin is protruding, and that will indicate how much wear we've got on the brakes. Make sense?
Yes, Sim. Thank you.
You sure?
Yes, Sim.
Okay. Yeah. So that's our adjuster. Yeah. It's just one example of an adjuster, but it just runs through. Operation: movement of the piston or the pressure plate transmitted via the retraction pin and the friction bush to compress the adjuster. Moves the guide until it abuts against the torque plate. Yeah, so pulls that green guide back, compresses the spring. Yeah. Clearance between the guide and the torque plate is the designed running clearance. Yeah. As the wear takes place in the discs, the pressure plate has to move further forward, pulling the retraction pin through the friction bush by the same amount equal to the disc wear, but maintaining the design clearance when the brakes are released. And it says on some brakes, not all, but on some brakes, the wear may be assessed by measuring the protrusion of that retraction pin. If you're checking brake wear, it's always got to be done with the brakes on, brakes applied. But we won't get too bogged down in the adjuster. Yeah, your wear indication. Yeah, you can see hopefully the pin just protruding there where the arrow is, and it's that pin that it's going to get pulled more and more through the torque plate as the brakes wear. Yeah, and it'll get down to a certain point. Put the brakes on. If you've got, I don't know, 2 millimeters protruding, then the brakes are water limits, and we need to change them. Badoom. Everybody okay with that? Got to admit, I'm not so keen. That's a very busy picture. It's meant to be a chop through of a brake unit. Showing the piston, showing the adjuster, showing the rotors and stators. Lock nut on the end. Transducer is there to measure wheel speed for our anti-skid. We'll talk about that after lunch. Yeah, some aircraft have got a brake temperature monitoring system on them. Temperature sensor at the wheels supplies information to the warning page on the flight deck. Just let me click back a bit now. Sorry, again, that's what it's talking about with the brake temperature indication. Yeah, typical system. Temperature sensor at each wheel supplies information to a central monitor. Monitor looks at temperature. Yeah. Button for each wheel. Yeah, records the temperature of the hottest brake, and the button illuminates when the associated brake temperature exceeds a predetermined amount. Yeah, so again, just another example. Yeah, we've got our tyre pressures and the brake temperatures. I'll come back to this in a minute when we talk about indication, but it's just to give you an idea of what it's on about. Yeah. Bleed in the brakes, yeah. We talked hydraulics, we talked air in the system. If you get air in your brake system, the brakes are just going to be totally inefficient. Yeah, very, very sluggish, less efficient, less effective. Yeah, so air in the system, as it says there, degrades the performance of the brakes. Sluggish is a good word that often appears. Yeah, if a response is sluggish, it's very, very slow. Bleed in the brakes, yeah, we're just taking air out using the bleed points on the brake. Yeah, brakes normally have an accumulator associated with them. Yeah, so if you're working on the brakes, make sure that you discharge the accumulator before you disconnect anything. Yeah. Testing the brakes, needn't worry about that. Yeah, we're just going to jack the wheel up, rotate the wheel, and put the brakes on and off. And if they're working, we're on a winner. Yeah, just make sure that the release. Large modern aircraft use a hydraulic brake system that receives its pressure from the main hydraulic system. Backup systems provided in case of failure. And they'll take hydraulic pressure from an alternate source. High pressure brake systems use the normal aircraft hydraulic system to provide pressurized fluid. Brakes applied by using the toe pedals attached to the rudder bar or by a handbrake lever for parking. Accumulator normally provided to provide a reserve of fluid in case of total hydraulic pressure loss. We can use the accumulator as an emergency. Yeah, and we'll get so many applications out of the brakes. System connected to a brake metering valve or a brake control valve. That's operated by the foot pedals, and that brake control valve allows the pilot to vary the pressure being supplied to the brakes. The more he presses, the more pressure is going to get through. Right, it talks about a bogie system, yeah, and a typical brake system. And it says that the normal brake system powered by the right-hand hydraulics and backed up from the left-hand system. Accumulator in there, if we have total hydraulic failure, we've got a store of pressure operated by the brake pedals, the foot pedals. But with the accumulator, we're kind of limited to the amount of applications we get. Parking brake, depressing both pedals, then pulling the parking brake handle. And the brakes are then held in the on position, and the brake pedals will be in the on position. Anything else there that we need to worry about? No. Typical brake system. Yeah, your foot pedals. Yeah. As the pilot presses his pedals, there's a little cylinder at the back of the pedals that transmits hydraulic pressure down the brake control valve. The brake control valve will then open the lines to the brake units. Yeah. Left-hand system, right-hand system, accumulator in each, so we needn't worry about that. We know about those. The main system pressure is normally going to be too high for the brakes, yeah. So we need to reduce that pressure. So when we run the main system pressure, it will go through a debooster, and all a debooster is a pressure reducing valve. It just brings the brake system pressure down to a more usable level. If we've got anti-skid in the system, yeah, again, the brake pressure is going to go through the anti-skid modulator. We'll look at anti-skid after lunch, and then via the anti-skid unit to the brakes, and we'll apply the brakes. Dead simple wee system. Monitoring the temperature, we've just talked about that. Right, that bit at the top of page 116, brake temperature monitoring, which is what I was trying to show you earlier. The ICAS display will show the brake squares with a number representing units 0 to 9. And those numbers equate to the amount of heat at the brake. Yeah, a blue or white square will surround each square. If the brake is overheating, that little surround will turn white. Yeah, so white indicates a brake overheat, blue is normal. Yeah, so that's our brake temperatures. Yeah, we've got the normal range. Yeah, gives us an idea of what the temperature is at the brake units. Nice, it calls it cyan blue. Yeah. If we get an overheat, yeah, the box will turn white. Yeah. If we're in the normal range, it says the box is white for each brake that exceeds 2. 0 to 2, the sort of accepted range. 5 to 9, just to highlight the box numbers, both turn white. Yeah, but white indicates brake overheat. That's what we need to highlight at the top of page 116. 116. Yeah, your brakes, your multi brakes. Yeah, again, I don't propose to go through the schematics. We don't need to. It's just showing you that we've got power coming in. We've got auto brake facility. We'll cover that later. We've got parking brake. Yeah, and then via your anti-skid to your brake units. Yeah, the alternate side of things. Yeah, we're just going to take our pressure from a different source. Yeah, and again. Via the various components to apply the brakes. Page 116, back to the text. The purpose of the anti-skid system is to monitor wheel deceleration and provide a brake release to achieve optimum braking under varying conditions. What happens if the wheel slows down too quickly? It's going to start skidding along the ground. It's going to start sliding. So what we need to do is to release the brakes to allow the wheel to rotate. And we do that using the anti-skid system. So the anti-skid system and the brake system are tied into each other. Yeah. Normal and alternate anti-skid valves receive brake pressure from the normal or alternate brakes valves. Depending on which system is being used, anti-skid valves controlled by the anti-skid system. Yeah, and the anti-skid will release the brakes if the wheel slows down too quickly. Means it's locking up, it's not rotating, and that could lead to a tyre burst. Once the wheel's rotating, it's back up to an acceptable speed, acceptable rotation, then the system will reapply the brakes again. Control unit also provides touchdown and aquaplane protection. Yeah, take that with a pinch of salt to say it does. If we get a fault in the anti-skid, yeah, we're going to get a light on there. Is there anything else I need to say? We're going to go through anti-skid after lunch anyway. So we don't need to really worry about the anti-skid at the moment. Auto brake is designed to relieve pilot workload on touchdown and provide consistent and smooth brake application for passenger comfort. So what happens is that the system will automatically apply pressure to all the brakes to slow the aircraft down at a rate selected by the pilot. So depending on the length of the runway, yeah, the pilot can select on his auto brakes a particular figure, yeah, and that will give the optimum amount of braking for that length of runway. If, however, it all goes horribly wrong, the pilot can override it by pressing on the brake pedals. Auto brakes controlled through the auto brake selector. Yeah, we'll see that in a moment. Yeah, and then there's the just the examples of the systems and the operation in them. As I say, I wouldn't get myself too bogged down in the actual schematics of the systems. Yeah, the schematic. It's just to give you an idea of what's in there. Standard brake pressure gauges, the triple axis indicator. We've got a little gauge at the bottom that's telling us what the accumulator pressure is for the brakes. The brake gauges are there to show what pressure is being applied from the foot pedals. So if I press the foot pedals together, the two indicators should show me what pressure I'm applying to the brakes. I don't need anything else off there. Not really. This thing we've already chatted about. The brake temperatures, yeah, and if over temperature, the box will turn white, and the text might turn white. In this case, probably a bit confusing. But yeah, brake temperatures. Yeah, go with what it says in the text. Yeah, if the brakes are overheated, the indicator will turn white. So the white box around the lettering. Just like that. Yeah, so brake temperature shown on the ICAS, relative value of the wheel brake temperature, 0 to 2 the initial range, box and number are blue. Anything out that, anything out with the thing will turn white is what we need to know. Happy days. Auto brake. Yeah, the auto brake selected by the pilot prior to landing. Yeah, depending on the length of runway that he's got, he'll make his selection, and that allows the aircraft to apply the required amount of brake pressure. As I say, if he presses on the brakes, he can override the auto. Off selected, different length of runway for optimum braking pressure, maximum braking, and there's a rejected takeoff selection as well. don't think there's anything else we need to worry about. If the system's inoperative, he'll get a warning light next to it to tell him. Yeah, and just over braking. Yeah, if anti-skid's not working. Anti-skid doesn't work, the brakes lock up. Yeah, the tyres just get scuffed away, and eventually they'll go pop. Just another schematic, typical anti-skid auto brake system. Again, I don't want to get too bogged down in all this lot, but the anti-skid system, the auto brake system, both feeding inputs in. Yeah, the anti-skid looking after particular sets of wheels. It'll be monitoring what's going on. The auto brake, yeah, the auto brake will feed in there as well from our hydraulic system, through the brake valves, to the auto brake shuttle, yeah, to the auto brake input, to the anti-skid valves. The anti-skid valves monitoring the wheel speed and saying whether the brakes should be on or off. So the anti-skid modulates the application of the brakes to make sure that we don't enter a skid. I don't think there's much else we need to know about there. Twin wheel system. Let's just see where we are. Won't be a second. Oh, it should be about 180. Sorry, just bear with me a moment. Yeah, we'll just get this a little bit out of the way and then we'll stop for lunch. Yeah, anti-skid, we've been through that. We'll touch anti-skid again after lunch and we'll find out the components. It's there to prevent the wheels from locking up. Auto brake designed to relieve pilot workload on touchdown, provide consistent smooth brake application. Automatically applies pressure to all the brakes to slow the aircraft down at the rate selected by the pilot. Yeah. Anti-skid and the auto brake operate through an auto brake module to provide metered pressure to the brakes through the normal anti-skid valves. Brake pressure varies according to the rate of aircraft deceleration selected and the actual rate of deceleration obtained through braking, thrust reverse, and ground speed. I'm just trying to think back. He selects auto brake, and I can't remember whether he's pressing the pedals and the auto brake is delivering the required amount of pressure, or whether he's got his feet off. I'll double check that. I genuinely can't remember offhand, but I'll double check that while I'm having my lunch. But anyhow, all we need to know is the auto brake is going to give him the required amount of pressure for a selection that he makes. Twin wheel system, yeah, twin wheel brake system receives pressure at what's that, about 2,500 from the main or the auxiliary hydraulic systems, divided into two subsystems. Non-return valves isolate one system from the other. In the event of a leak, each system can be isolated from the supply by electrically operated valves. Yeah, wonderful. One system supplies pressure for brake unit operation on the inner wheels, while the outer wheels from the second subsystem. In the event of one subsystem failing, we've got half the normal braking power available. Equal braking can still be applied, but it'll be less effective than the normal. Each system with its own accumulator. Accumulator is initially charged, yeah, 1,300 PSI, we'll forget that. Manually operated pressure release valves allow accumulated pressure to be dumped so we can carry out maintenance. And pretty much that's that. What we're saying, 4-element brake control valve. Yeah. So we've got the brake control valve here. From the main supply, Yeah, hydraulic pressure down to the brake control valve. The accumulators are there, yeah, to give you your damping and a store of emergency pressure should we need it. Yeah, pressure relief valves to dump the accumulators, brake isolating valves so we can work that system should we want to. The brake control valve, yeah, is going to direct pressure to the selected brake unit, whichever one we're going with. Yeah, some for the inner, some for the outers. Yeah, so master cylinders from the first officer and the captain. At the back of the rudder bar, the toe pedals. Yeah, it'll press his toe pedals, and by pressing the toe pedals, that is going to open up the main system pressure to the relative brake units. Yeah, the brake units will be the pressure will be reduced to a working level, and then the brakes will be applied. The anti-skid system will be looking at the rotation of the wheel, and the anti-skid system will release the brakes should it sense a skid. So your 4-element brake control valve, hydraulically connected to the master cylinders. Master cylinders are completely self-contained, not connected to the main supply. Basically, we're just using hydraulic pressure from the foot pedals to open a valve in the brake module, or the brake control valve. Yeah, control valve senses the pressure applied to the master cylinders. Control valve delivers proportional hydraulic pressure to the appropriate brake units. That gives us differential braking. So if he presses his left-hand pedal, that will just put pressure to one brake unit. If he presses them both together, it'll apply pressure to both brake units. We can have a parking brake facility on there as well. Pull the parking lever, press the brakes, or press the brakes, pull the parking lever. That's just going to put pressure to all four. Anti-skid we've already mentioned. Modulator in each brake supply line to reduce the system pressure. Pressure loss during max Surrett operation. Yeah, just make sure that we've got brake pressure there for the next application. We'll look at that. Accumulators, we're happy with those, I am assuming. Accumulator pressure in one of the systems falls below 1400 psi. Pressure switch will give a brake slow caption in the cabin. Yeah, and then just by looking at the triple gauge, we can see which system's got low pressure. Failed system can be isolated by switching it off. Brake control valve, pressure reducing valve basically. Controls pressure in the brake system according to the position of the pilot's pedals. Yeah, the harder he presses, the more brake pressure he is going to apply. So the brake control valve, yeah, the more he presses, the more it's going to allow pressure down to the brake units. Yeah, so light braking, heavy braking. Anything else there? No, we've done all that. The pressure relay transmits fluid pressure to a direct reading pressure gauge or to a pressure transmitter, which will electrically indicate in the cabin. So you've got your direct reading gauge or your pressure transmitter. Pressure gauges, yeah, depending on the type of aircraft, depends on the gauge you're going to get fitted. Electric gauge, digital gauge, direct reading gauge. Pressure switches there to monitor the pressure and illuminate if we get a low pressure. Put a warning light on. I know I'm whistling through this, but there's genuinely nothing that we need to worry about. As we say, warning light if things on, isolation, brake control valve we've talked about, foot brake actuator, pressure relay, pressure gauges, pressure switches. We know what they're all about. We've done that. Yeah, so now that's just the system built up. Yeah, self-contained. Press the pedals, the master cylinders. That opens a valve in the brake control valve, which reduces the pressure, or the debooster will reduce the pressure down through the anti-skid modulator to the brake. We've got the accumulators in there. We know about those. Pressure switch, put on a warning light if we get low pressure. Pressure relay or pressure transmitter is going to send a signal up to a gauge so we can read what's going on. Yeah, your triple gauges, as we say. Press the pedals. Yeah, that's going to indicate what pressure you're going. You got your accumulator pressure. If we get a low pressure, yeah, we'll get a warning light. We can look at the triple gauge and see which system has dropped. Isolation valve if we need to do any work. And the brake temperature and the brake temperature monitoring. Yeah, we can have a look and see what the temperatures are. I think it did say, didn't it, about monitoring the pressure of the temperature at the highest brake unit. God. Brake control valve, yeah. Again, we don't need to go into the internal workings of the brake control valve. But basically, from your pilot's pedal or your second pilot's pedal, pressure is going to operate a wee piston. Yeah. Notice the spring in there, so once we release the pedals, the thing will go back to neutral. But as we press on the pedal, that pedal is going to push down on a plunger. Yeah. As we press down on the plunger, we're opening the inlet port to the brakes. Fluid flows through the brakes. Yeah, the more the harder we press, the more we're compressing a spring. Yeah, and the more fluid we're allowing through. Release the brakes. Yeah, take your feet off the pedals. Cradle push up. It'll shut off the inlet port, and at the same time, it's the pressures come off that cap because you release the pedals. This little valve cap's going to operate, and it's going to allow the excess pressure away to. It says exhaust there, away back to return. Yeah. Foot motors. Yeah. Again, they're self-contained. Again, we don't need to go into the ins and outs of them, but basically, a self-contained actuator, as I press down on the foot pedals, yeah, the top of the thing is top of the cylinder is being pressed down. As that gets pressed down, it's transmitting pressure to the brake valve. Yeah, release the brakes. Yeah, that will shoot back up again, and it'll seal off the input to the brakes. What's the relay valve doing? Yeah, just allowing us to take pressure from the brake system. Yeah, and we're going to transmit it upstream to a gauge or to a pressure transmitter. Yeah, so the harder I press, yeah, more I'm going to push the fluid through, so that fluid pressure is going to be transmitted. If I get a failure or a leak upstream, yeah, the pressure acting on the brake system is going to push that piston up and seal the relay valve off. So not only is it transmitting pressure, but it'll act as a fuse if I get a leak upstream. Yeah, the brake modulator, yeah, is there to reduce pressure. Not reduce pressure. It's the modulator, used in conjunction with the axle-mounted mechanical anti-skid unit in the brakes, allows full flow to the brake units on initial application and thereafter a restricted flow. So on initial application of the brakes, we're going to get full application, and then afterwards we're just going to get a trickle feed of pressure through the brakes. So the modulator, during initial operation of the brake control valve, the piston's forced down against spring pressure, the brakes are applied. Subsequent fluid feed to the brakes, called for by the anti-skid unit operation, is through that restricted orifice and is limited. Limited flow allows the anti-skid to release the brakes, but make sure that there's sufficient pressure there to reapply them as soon as we're back up to the required condition. So that's your modulator. Works with the anti-skid. So initially we'll push the brakes on. And that initial pressure, apply the brakes. If the anti-skid releases the brakes, because of that orifice, we've always got a head of pressure there, and the brakes will reapply as soon as the anti-skid wants them to. Just make sure there's nothing else there that we're not missed. So modulator, page 129, in conjunction with the anti-skid units. The debooster is a pressure reducing valve, and reduces pressure down to a usable level. Operate on the basis of a pressure differential. Don't need to worry about that. But the function of the debooster, to reduce the pressure. So pressure acting on a small piston. That pressure acting on the small piston, because of the larger volume, the larger area, the pressure that's being applied to the brakes is reduced to the usable level. The other thing we can do with the debooster, we can use it to top up the brake system. So by breaking in the brake system, applying pressure, eventually we'll push down on this, I'll call it a cradle, I can't think of the right name. So it'll push down on the cradle. As the cradle pushes down against a spring, there's a fixed piston with a little ball on the end. The piston, nose of the piston, lifts the ball up, and that allows fluid to flow through to top up the wheel brakes. Once I stop putting pressure in, the cradle's going to go back up, and the ball will seal it off. The pressure required for filling it is going to be different to the pressure for operating the brakes. So the cradle won't operate the brakes until the cradle won't operate the brakes during normal operation. That's what I'm trying to say. Right, that is a good place to stop and have lunch. If anybody's got any questions on any of that lot, I know I've glossed over some of it, but the bits I've glossed over we don't need to worry about. However, if anybody's got any questions at all, give me a shout after lunch. 12:30 my time, so 13:30 your time, my time. So 1 hour for lunch, please, guys, and then we'll try and get this wrapped off. Okay, and any questions that you think of, give me a shout after lunch, and I'll try my best to answer them. Okay with that?
Good, Jim.
Okay, Jim.
Okay, right. See you in a few minutes. Right then, guys. Hope we're all fed and watered, happy. Before we plod on with the rest of the landing gear, then, has anybody got any questions at all on what we did this morning? Anything at all?
Is there any highlight part from maintenance?
All the bits that I said to highlight, we've been through. Said to highlight them at the time as we were going through the book.
Yes, yes. You didn't told anything. In maintenance section, you didn't told any highlight.
Not in maintenance, no.
Okay. Okay, then that is fine.
Maintenance is all fairly
Follow the
self-explanatory. The only bit you need to think about that I can think of is when we did shock absorbers, when we were talking about dimension X. Yeah. Yeah, that's the only bit of maintenance that I can think of. We talked about the shock absorbers, making sure we know the different types. Got an idea of how they work. Dimension X, using the pressure extension graph, the liquid spring, the differential areas giving us our sealing. Yeah. So it doesn't matter which way the shock absorber is compressing or extending. The pressure that's being applied to that gland seal, because of the differential areas, it's always going to be sealed. We could spring brakes. Yeah, we shot through brakes. Not a lot to really say about the brakes. How they operate. Yeah, the stators, the rotors. Rotors dragged around by the wheels. Stators stay with the torque plate, which is attached to the axle. When we apply the brakes, hydraulic pressures, piston pushes against the pressure plate, and between the pressure plate and the thrust plate, the stators and the rotors get squeezed together. We convert kinetic energy into heat energy, and that heat energy is dissipated by various means, by the vents in the wheel, by a fan in the axle. Heat shields protect the wheel from the heat of the brake unit. And the brake itself, the materials it's made out of, will absorb heat. They say that carbon's probably the best one. It's a very, very good heat sink for the weight. And we said the only thing to watch with carbon is all the dust that's generated. Indicator pin telling us how worn the brakes are. And remember, if you're checking for brake wear, you need to have the brakes applied. Yeah. As the adjuster, we can use the pin as an indicator, but we don't have to. We can have a separate indicator if we want. But as we apply the brakes push the pressure plate, which in turn pushes the pin, and the pin goes through a friction bush, which will grip it tight. Yeah, as the pressure plate moves down, because that friction bush is being gripped, the spring is compressed with that guide. When we release the brakes, the spring will push the guide back up. And the pin, as the spring pushes the guide back up, that will pull the pin, and it will pull the pressure plate away from the brake, but just by a nominal clearance, that sort of clearance, to make sure that the brakes are rotating, or that the wheels are rotating freely. But as soon as we reapply the brakes, there's going to be near enough an instant response. Indicator pin. We mentioned that, but make sure you got the brakes applied. I suppose typical brake system. We looked at a couple of examples. Don't forget the accumulators are there to act as backup. And the size of the accumulator limits the amount of brake applications you'll get from the system in an emergency. Before you get to the accumulators are pretty much a last resort. There'll be an alternate operating system, be that from an emergency hydraulic system, an alternate hydraulic system. Then we looked at what the different components did. We'll run through those just to make sure everybody's happy. Don't need to worry about the circuit diagrams. Indications, we've got the indications for the brake system, the triple gauge, which tells us the amount of pressure we're applying to each individual brake, and below that we've got the system pressure available to us, which reflects the pressure that's sitting in the accumulator. The over temperature readings, we said that they're normally going to be blue in colour, but if we get a brake over temperature, they're going to turn white. The auto brake, pilot's going to select whatever he wants for the length of runway probably that he's got, the amount of braking that he wants. He'll work all that out and he'll make his selection. And it just means on landing that he doesn't have to do anything. He can concentrate on other stuff. However, if he needs to press the brakes, him pressing the brakes will override the auto brake. The rejected takeoff, he can select that before he goes flying. So if anything does go wrong, during the takeoff run, if it becomes a rejected takeoff, then that braking is there for him as well. The aircraft will monitor different parameters. Warning lights for that and the anti-skid. We'll look at anti-skid in just a minute. That's what happens if your brakes jam up. Typical system, typical twin-wheeled system. The components that are in there. Switches, indicators, warning light if we lose pressure. We can isolate sections so we can carry out maintenance. Brake control valve, the brains of the outfit. Foot brake actuator, self-contained, and all that's doing is sending a signal down to the BVM. The relay, transferring pressure to a direct reading gauge or up to a pressure transmitter, which will put on an electric gauge. Your pressure gauges are in there so we can see what pressures we've got in the brakes, and pressure switches that are going to trip the warning light if anything goes wrong. And that was them all in the system. The indicators that we've got, the triple indicator, operating your brakes, press the brake pedal, and we can see how much pressure we're applying to the brakes. Press both pedals together, you'll get hopefully the same. If we're using differential braking, it'll show us what we're doing there. That one's showing the outer and the inner brakes, what pressure's going to them. Anything else we need to know there? No. The brake control valve, we looked at that very briefly. Don't need to worry too much about it. Apply the brakes, press down, plunger presses down, seals off the outlet, inlet port opens, and the inlet port opening, again, pushing down on the what's it, and that pressure being transmitted to the brakes. The harder we press, the more pressure is being applied to the brakes. Release the brakes. The inlet valve will close, and as that closes, stops the brake pressure coming in. The exhaust cap will lift and it'll relieve any excess pressure back to exhaust, so the brakes will release. That was just our foot motors, and basically all we're doing is just compressing oil and pushing that oil that's going to open a valve in the brake module. Or as we saw, we press on the foot pedals, and it'll just transmit that pressure down to here. If the co-pilot does it, again, that pressure will be felt there. Spring loaded, so it'll go back to a neutral. Parking brake facility, put the brakes on, press the pedals, that'll apply the brakes, pull the parking brake handle, and that'll hold the brakes in the on position. The relay valve, as we said, that's just passing pressure from the brake system off to a gauge or a pressure transmitter. So as brake pressure is sitting there, it's being felt here, so it's being felt up the line. If we get a leak up the line, the relay valve will seal off the brake system from the upstream, so we're not going to get a loss of pressure. Modulator there for assisting the anti-skid, so it's going to make sure when we apply the brakes that there's full brake pressure applied. And then there's always going to be a trickle feed of pressure, so if the anti-skid releases the brakes, when it goes to reapply them, the brakes will reapply pretty much instantly. Debooster, pressure reducing valve, posh name for a pressure reducing valve, and it just puts high pressure on a small piston area, and that small piston's got a large area underneath it, and it's the large area, obviously larger the area, that's going to drop the pressure down, but that reduced pressure is still going to operate the brakes for us. Everybody okay with that? Anybody got any questions at all on that little lot?
Hello, Jim.
Hello.
Uh, can you please again describe this this thing, liquid spring shock absorber?
Yeah. Liquid spring. On page 98. The liquid spring, yeah.
Yes.
It's a special oil in the liquid spring that is compressible. Yeah, generally oils don't compress, but in the liquid spring we're going to use an oil that does. So liquid springs full of this oil. Yeah, piston attached to your wheel. Yeah, aircraft lands. Yeah, that piston is going to get pushed up into the body of the liquid spring. As it gets pushed up, the fluid that's in the top wants to get through to the bottom. So in the piston, yeah, there's a little valve. So now as the piston's going up, the oil tries to come through. It presses down on that valve, opens the valve, and now the oil can flow from the top chamber to the bottom chamber, as well as coming through that wee orifice there. Once the leg's compressed, yeah, you got the bulk of your oil in the bottom. That leg wants to try and extend. So now as the leg's extending, the piston head's trying to come down, but you've got all that oil underneath it. The piston can only extend as quickly as the oil goes through that little orifice there, that hole.
Okay.
Yeah.
Okay.
Because it's coming down the way, that valve is sealing off, assisted with spring pressure. So there's nothing to force that valve open. That valve closes. So now your oil is just going up through the orifice.
Okay.
Yeah?
Yeah, Jim. So it has only that synthetic silicon-based fluid. No
Yes.
nitrogen. No nitrogen.
No, nothing like that in it.
Okay, got it, Jim. And what is this? Please explain this also, Jim. Piston rod sealing.
That's what I was skipping over, but yeah. The piston rod, yeah, that's your piston rod, and the seal underneath it. We've got a pressure plate and a gland ring and a backing plate. Yeah, and there's a series of set of dowels screwed into the pressure plate. Yeah, so the gland assembly prevents leakage of the cylinder whatever the cylinder pressure is, and it does that by the principle of differential areas. Yeah, the liquid in the spring, yeah, for example, with a cylinder pressure of 10,000 psi. So in the actuator we've got 10,000 psi. If the pressure plate has a surface area of 5 square inches, force acting on it, 10,000 times 5, 50,000 pounds. Yeah, that force will also be acting on the gland ring. That's your gland ring there. That's your pressure plate there. So if you've got 10,000 pounds in here, you with me? Yeah.
Yes.
10,000 pounds, 5 square inch area, 50,000 pounds acting on it that way. That force acted on the gland ring, yeah, but because of your difference in areas, yeah, because it's got the 2 holes in it, yeah, that's only got an area of the example says 4 square inches. So the pressure on the gland ring will be 12,500 psi. So the sealing pressure is exceeding the cylinder pressure by a ratio of, in this case, 5 to 4. You okay with that?
Okay, Jim.
Yeah. In this case, sealing pressure will be 2,500 psi. On compression, as the cylinder pressure increases, so will the sealing pressure. So all it's doing is using the differential areas. So the cylinder is going to be charged to a pressure. The oil in there is going to be pressurized anyway. but just to make sure that the thing doesn't leak. Yeah, we're applying pressure on the pressure plate. We're applying pressure on the gland ring.
Okay, Jim. Okay, Jim.
You okay with that?
Thank you. Okay.
You
Jim.
sure?
Sure, Jim.
Okay. Right. Anybody else while I'm up this way? Bricks went through, and now we're on anti-skid. Anti-skid units there. Yeah. The purpose of the anti-skid is to prevent skidding. Let me just find my page now that I've skipped ahead.
101. $131.
131. Yeah, that's lovely. Thank you. Thank you very much. Yeah, purpose of anti-skid to prevent the aircraft from skidding. And what skidding is where the wheels stop rotating. Yeah. So what we want to do when we're braking, we want the wheels to be rotating, but we want the brakes to apply sufficient pressure to slow them down. Yeah. Rather than just slamming them on, we're just going to slow the aircraft down. If we allow the skid to take place, then obviously tyre bursts and all the rest of the stuff, and that could be dangerous to the aircraft and to the passengers. So most of our larger aircraft have anti-skid units fitted to them. Two types that we'll come across: the mechanical anti-skid unit and the electronic anti-skid unit. Often referred to as maxarettes. Yeah. So the rim division, or the mechanical unit. Yeah. Again, we refer that to as a maxarette unit. There's a little wheel, yeah, that contacts with the rim of the main wheel. So as the main wheel's rotating, this flywheel on the maxarette's rotating. Yeah. As the flywheel's rotating, if it's going at the same speed as the main wheel, there's not a problem. If the main wheel slows down suddenly, yeah, within the maxarette wheel, there's a flywheel, a weight, if you like, that's rotating. Because of inertia, yeah, if the outer wheel stops turning, the flywheel inside is going to carry on. And as the flywheel carries on, it's going to open a return valve to release the brake pressure. Once the speed of the flywheel catches back up to the speed of the main wheel, that exhaust valve will close, or the return valve will close, and that will allow brake pressure back into the brakes. So that's the thing, the hydraulic side of it, yeah. Inlet for the brakes, little block containing our valves, yeah. The wheel containing the flywheel. Mount the two together, and a plate so we can mount it onto the main wheel, and that's what we're looking like. If you can imagine that rubber tire on the maxarette unit. So when if I say rubber tire, I'm referring to this bit here, and it's this bit that contacts the rim of the main wheel. Yeah. So you got that little rubber tire. That's the rim of the main wheel. So as the main wheel is rotating, this thing is. Inside here, we've got this flywheel, yeah, which is sort of weighted. So as the whole wheel's rotating, everything is fine. Yeah. If the main wheel stops or slows down dramatically, starts to enter a skid, what happens, because of inertia, that flywheel is going to carry on turning. And with that flywheel turning, there's two little ball bearings inside, or a series of ball bearings. They lift up in a groove, and they press against the little valve here. That little valve operating will again in turn operate a wee lever, and that will open the brakes to return. Yeah. So as that travels up, it's let's see if I've got a better picture. I thought there was a better picture than that. Obviously not. That's your flywheel. Yeah. So your drum running round, your flywheel running round, deceleration of the shell, the tired bit. The drum will carry on rotating. Yeah. Inertia of the flywheel causes it to be displaced relative to the drum at 60 degrees in the direction of rotation. So it's whacking round. Yeah, these little ball bearings are sitting in a little groove, if you like. As the flywheel carries on turning, yeah, the main wheel, the outer shells stop. The flywheel carries on turning. These balls are driven up the little channels. Yeah, so they ride up what they call the cam profile. Yeah, riding up the cam profile moves the wee thrust rod, that thing, and as that thrust rod moves, yeah, what it's doing, it's closing off the inlet valve to the brakes, and it's opening up the exhaust to return. Yeah, so that's what we're talking about before. It's sitting there, fat, dumb, and happy. Everything's rotating normally. The ball bearings are where they should be, and the wee valves in its position. Yeah, so it's taking in fluid. The inlet valve's open, and it's allowing. Sorry, I've gone the wrong way there. The inlet valve's open, and it's allowing pressure through to the brakes. Yeah, wheel slows down. Yeah, the cam, the balls ride up in the cam, allows that valve to move, and that in turn via the linkage is shutting off the inlet and opening the pressure line to return, which is going to release the brakes. As the wheel speeds up again, yeah, the Maxarette outer rim starts turning, and as it does, the ball will ride back down the cam into its center position, and in doing that, the valve will open again. It'll close off the exhaust and open the line up to the brakes. So as the Maxarette's rotating, it's applying and releasing the brakes depending on the speed of the wheel relative to it. Yeah, not a lot else to say about that, quite honestly. Is everybody okay with that? The mechanical one, known as the Maxarette unit.
Hello, Jim.
Yeah.
In this diagram.
This one.
Yes, this diagram.
Yeah.
That what I am not able to understand is that flywheel is not directly connected with that wheel, that rubber wheel.
No.
No. Flywheel is this unit is rotating with the hub. That unit, and inside that there is a flywheel.
Yeah. So if that's your main wheel, yeah, okay. The Maxarette is connected to the rim of the main wheel.
Okay.
Yeah. Okay. So as the main wheel's rotating, the Maxarette wheel is rotating. Inside there, you've got this flywheel. Yeah. Okay. So if the main wheel stops for whatever reason,
okay,
yeah, because the outer wheel on the Maxarette that stops rotating with the main wheel, but the flywheel inside it will carry on
rotating.
Yeah, yeah, and because the flywheel inside carries on rotating, the outer bit stopped. or effectively stopped, what happens is the little ball bearings in there ride up a channel. Yeah, there's a little cam in there, a little channel, and the balls ride up on there. And as they ride up, again, if you can imagine, that's the end of your blue valve. Yeah, your ball would normally be held in that position, but it's which way around is it? Just trying to think which way it goes. I think the cam that it rides in is that sort of shape. So as the flywheel carries on rotating, yeah, the ball bearing is driven up the cam, and that allows the valve to move, the valve to open.
Okay.
Yeah.
But that flywheel, Jim,
yeah,
that flywheel, even if that max rate unit is rotating, that flywheel is still rotating inside it.
Yes.
So the max rate unit slows down because the wheels are decelerating.
Because the wheel slows down, that outer wheel on the maxarette will slow down. Yeah.
And the flyweight flyweight continues to rotate because of inertia.
Yeah.
And then it lifts that valve. Then it lifts that valve.
Yep, that's it. Yeah. So as that ball moves out the way, or rides up, it operates that that little plunger, if you like, the little blue bit. That as the ball rolls up, yeah, it causes that to operate, and as that operates, it's going to seal off the inlet, yeah, and open the return line. So your brake pressure is going to go back off to return. As the outer shell increases in speed, yeah, it's going to catch up again with the flywheel, and that's going to cause the ball to return to its original position, which is going to allow this to move back, assisted by a spring. As that moves back, it's opening the brake line up. Yeah, so your pressure's now coming in.
Okay, Jim.
To the brakes. So can you see from that one? Yeah, everything working quite sweet. Everything's happy. The ball's sitting in the centre. Yeah, this is what it's calling the cam profile. Ball sitting in the centre, and the valves open. So pressure coming in from the brake control valve through the inlet valve and off to the brakes. As the outer rim stops turning, yeah, the flywheel carries on. The ball bearing rides up the car. You can see the little channel. That's what I was trying to draw there. So it drives up there, which in turn allows the valve to move the linkage, and the link mechanism, yeah, seals off the inlet, and at the same time it opens the outlet, so your brake pressure is ducted off to return. Okay with that?
Okay, Jim. Thank you.
Lovely. We can have an axle mounted. That was a rim mounted maxarette. Probably one of the more common ones nowadays is the axle mounted. Yeah. Sorry, I'll just catch up with my page. The axle mounted anti-skid unit, it lives inside the axle of the main wheel it's associated with, and is driven from the wheel hub by a little flexible drive. Yeah, so a little flexible drive from the wheel hub into the input shaft in the maxarette there. Similar sort of affair in as much as we've got a flywheel that'll keep on turning, but we've got a lot of gearing in there to bring the speeds down to workable levels. Yeah. Unit contains components similar to the rim-driven Maxarette, but its mechanism includes a ring, sun, and planet gearing and a clutch. Units driven at wheel speed. The gearing is necessary to step up the speed of the flywheel to give it the momentum it requires. The clutch is there for starting torque. Don't need to worry about that. Input shaft via the clutch gear train. Yeah, the drive spring grips the drive ring. Positive drive to the flywheel. In this condition, the two thrust bearings like the base of the profile of the cam. Where's your little thrust bearings? Yeah, a couple of thrust bearings there. We've got the valve mechanism, the valve thrust rod. You've got your return line, operating valve, and your brake pressure line. So the flywheel, yeah, is the way the thing's set up. The flywheel is going to be rotating at the same speed of the wheel because of the gearing and the speed that the input shaft's going at. Yeah. Should the wheel decelerate as it's picking up a skid, yeah, it's going to decelerate quite quickly. The input and the main shafts of the unit also slow down, but the flywheel will carry on. Yeah, it'll overrun. It'll take the drive ring with it, and the overrun of the drive ring causes the two thrust bearings again to ride up a cam profile and move the thrust rod to open the valve to return. Again, not sure whether I've got a picture. Yeah. We're sitting in the axle. You've got the input drive shaft, yeah, your clutching mechanism, the gear train, and the drive ring. Yeah, the drive ring and the flywheel, yeah, normally held together. If the wheel slows down too much, yeah, there'll be a bit of a disconnect between the flywheel and the drive ring. Yeah, and that will allow the thrust bearings here to run up a little cam. Yeah, and it's the action of that cam riding up that's going to open the valve to return. It's not the best picture in the world. Fully appreciate that, but aircraft wheel decelerates to near skid condition. Main shaft drive shaft decelerates proportionately. The inertia of the flywheel causes the drive ring to advance in relation to the shaft. Yeah. Revolution of the drive ring forces the thrust bearing up the cam face. Yeah, and as that rolls up the cam face, it's opening the valve to return. As I say, I appreciate it's not the best picture in the world, but the principle, the rim drive and the axle-driven anti-skid units, the principle's the same. Yeah, what they're doing is they're just decelerating a slowdown in the wheel, and the internal mechanism is opening up the exhaust line, or basically the return line, is opening up the exhaust line and releasing the pressure from the brakes. As the main wheel speeds up again, yeah, then the little thrust bearing is going to return back down the profile of the cam, and as it returns back, it's going to close off the exhaust, so brake pressure can be reapplied. Yeah, not a lot else to say there. I think we've covered the mechanical side of it. Operation of the anti-skid unit can be checked connecting hydraulic and electric power to the aeroplane. Take the wheel hubcap off. Yeah. Put the brakes on, and then turn the anti-skid unit, and you should be able to see it releasing the brakes and reapplying the brakes. Again, it's a follow the manual check, but easy enough done. Yeah. Apologise for the quality of the pictures. They are pretty pants in there. Are we all okay with the mechanical Maxarette? Any problems there? No, all right, lovely. The electronic system, yeah, the electronic system is a doozy. Yeah, modern high-speed aircraft, yeah, more than one brake on each side, and all the brakes are controlled with one pedal. So if there was a problem, the pilot wouldn't be able to tell which one of the wheels begins to skid, and he couldn't take any corrective action. If corrective action isn't taken, yeah, a locked wheel will obviously scuff along and the tyre will burst. It says modern aircraft, small wheels, high pressure tyres, so they can be accommodated in a small space in the aircraft, yeah. Type of aircraft lands on a wet runway, pilot applies the brakes, the friction between the tyre and the runway is much less than the anti-skid supported brake. So the wheels lock and the tyre will aquaplane, skating along the surface of the water. So you lose all your braking action and directional control for that wheel. So for maximum brake effectiveness, the friction between the tyre and the runway surface should relate to the friction in the brake. Peripheral speed on the tyre should be slightly less than the speed of the aircraft. So the tyre is going to grip the runway and possibly slip just a little bit, but we're not going to scuff the tyres, damage the tyres. Yeah. Constant brake pressure after slip started, the wheel will begin to decelerate. Brake friction will increase rapidly, and the wheel will lock up and then skid over the runway surface. No braking available, really. So the anti-skid system on our multi-wheel things must have some sort of wheel speed sensor, so we can detect any change in wheel speed, work out what the rate of deceleration is and then we can work out what pressure's got to be released and where before the wheel starts to skid. The valves releasing the pressure have got to act fast enough to make sure that not all of the pressure is released before the next application, which, as we said before with the modulator, is allowing the brakes to reapply pretty much straight away. So what we've got in the system, yeah, we've got a control box, yeah, the brains of the outfit, and the brains of the outfit is talking to the anti-skid control valve. Yeah, the anti-skid control valve is dictating what the brakes are going to do, yeah, and the brakes are feeding back their speed via a transducer in the wheel, or a speed sensor as it calls it here. Yeah, obviously the wheel speed, the control box is monitoring that. Wheels slowing down too quickly, control box, right, anti-skid control valve, release the brakes. Yes sir, I'll release the brakes. Wheel transducer, yeah, the wheel's speeded up, control box, anti-skid valve, right, apply the brakes a bit more, brakes, apply a bit more, wheel transducer, this is what speed we're doing now. So the whole system is chugging away quite happily. As if the pilot wants to stop the aircraft in a minimum distance, presses the brake pedals to apply maximum braking. All the brake units receive maximum pressure. Any wheels should start to decelerate at a rate which would indicate a skid, the onset of a skid. That pressure to that brake is released back into the system return. Control circuit measures the amount of time required for the wheel to spin back up, and then it applies pressure again, but at a slightly reduced rate. And again, it's monitoring what's going on. If that reduced pressure causes a skid, yeah, we'll release it again, and then put in a slightly lower level again. Yeah. Application of the release, application and release process continues, decreasing the pressure until the wheel is back into its normal parameters. Yeah, wheel's not allowed to decelerate fast enough to produce a skid, and the correct amount of braking is applied for any runway surface condition. So even though the pilot is standing on the brakes, yeah, the anti-skid system is monitoring the speed of the wheels, and it is supplying just enough pressure to apply the brakes, but to prevent the wheel from entering a skid. What else do we need to know? The anti-skid system, yeah, it'll operate so long as it's switched on. So the anti-skid's selected on. It'll operate so long as the undercarriage is down. Yeah, and it won't kick in until we've gone through the WOW switches. It does allow a test to be carried out in the air, but we don't want the anti-skid working in the air. We want it working on the ground, so it'll go through the WOWs. And the wheels have got to be spinning above a certain RPM, otherwise the anti-skid won't work. Yeah. I'm just going to go through these bits. The anti-skid system, 3 components: the wheel speed sensors, control box, control valves. Yeah. DC wheel speed sensor tells you how it works. Mounted in the wheel axle, the shaft of the arm fitted with a blade. I don't know whether you've come across these. Basically, that's your hubcap. On the end of the wheel speed sensor, there's a little blade, yeah, and the little blade fits into a slot on the hubcap. So as the hubcap's rotating, obviously with the wheel, that blade is turning. That blade turning, the speed of the blade is translated into an electronic signal in the sensor. It's the electronic sensor in the signal from the electronic sensor that goes to the control box. Yeah. Yeah. Hey. Yeah. Faster the wheel turns, higher the frequency of the current. Control box used with AC sensor converts it into DC. The control valve, 3-port anti-skid control valve located in the pressure line between the brake valve and the brake cylinder. 3rd line connecting the control valve to the system return. Tells us how it works. Right, what we've got is within the control valve, we've got a little flapper. Yeah, remember the other day we talked about differential pressures and the little flapper valve. As that moves across, it's going to start to seal off the inlet to one side or the other. The speed sensor, yeah, sending a signal, and that's going to drive this little bloody flapper valve. And the little flapper valve is going to move one way or the other, and that's going to direct pressure to a slide, yeah, a spool. So as the pressure is building up on one side, let's say it moves that way, pressure is going to build up onto this side. It's going to move that spool across, and it's going to open up the line to the brakes. If it wants to release, it'll go the other way, and aided by spring pressure, the spool will move across, and the brake pressure will then dawdle off to return. It does go through and it explains all how it's working. Yeah, but essentially what's happening, that flapper valve is taking a signal in, it's moving one way or the other, and it's directing pressure to one end of the spool or the other. As it directs pressure to the spool slides over and is allowing pressure through to the brakes. It is a very, very quick way of looking over it. If you want to go through it yourselves and work out the internal workings, please feel free. Yeah, please feel free.
Hello, Jim.
Hello.
This internal working is important or not? We
No.
ask that A1, A2.
No, that's why I said if you want to read it yourself, you can, but I'm not going to waste my time doing it now. Yeah,
Okay.
all you need to know is that the control valve will take in a signal, yeah, and it will apply or release the brakes depending on wheel speed. Yeah, and that's
Okay.
just to give you a rough idea of how it's working. if I had time, I'd go through it all. It all depends on the pressures being sent. You've got differential areas on the spool and how much braking is applied and how it's released. But I don't need to go into all that. Yeah.
So exam point of view, this anti-skid operation is not so important.
The anti-skid operation is, but the internal workings of the valve aren't.
This okay, Jim. Okay, I've got it. Thank you.
Yeah. So they can ask you, how does the anti-skid system work, or what's happening while the anti-skid system's working, but they're not going to ask you what the pressures are at A4 and A2 and all the rest of it. Yeah.
Okay, Jim.
Yeah. Okay. Right. So the anti-skid, like I say, the control box. Yeah, control box sending the signal to the control valve. Yeah, and the control valve is then directing pressure through to the brakes. Yeah, the more the wheel slows down, yeah, the control valve, the control box is going to tell the control valve to back off. Yeah, to release some of that pressure. So it'll release it and then it'll reapply it at a slightly reduced rate. So that spool valve will be going backwards and forwards, pressure to the brakes and back off again. Where we're going there, yeah. There's a whole page on what's happening there internally. Not going to bother with that. Yeah, not going to bother with that. Wheel speed sensed by the control box. We said that. Brake pressure increases slightly. The wheel will slip beyond the point. It'll start to skid, so we can release the brakes and then wheel speeds up. Apply the brakes again at slightly lower pressure, and that gives the anti-skid. Yeah, it's going to keep the wheels, keep the brakes more efficient, and make sure we don't enter a skid. Your locked wheel protection is a secondary system that provides protection in the event that one wheel stops rotating when the others are still rolling. Yeah. The valve signal level provided much higher than for normal control signals. So if you got a locked wheel, the signal would open the valve and prevent the wheel from locking. Yeah, that locked wheel action removed at speeds less than 30 knots to prevent brake pressure being removed during low speed turning. The other thing that we provide is what they call touchdown control. And touchdown control tells the control valve to make sure that there's no brake pressure applied prior to touchdown. So if the pilot was landing and had his feet on the brake pedals, yeah, even as the aircraft touched down, the brake control system wouldn't be applied until the wheels are rotating at a particular speed. Having said that, if you find a pilot landing with his feet on the brake pedals, slap him. Yeah, it's just a recipe for disaster. They should all make sure that the feet are off the brakes before they touch down. Anti-skid, yeah, we can test the anti-skid system. Yeah, make sure it's working. If we get a failure in the anti-skid system, we'll get a warning light in the cabin. So test procedure in the AMM. Yeah, we're going to make sure that the wow switches are in the flight condition. Anti-skid switched off. Yeah, put the brakes on. Check the brakes come on. Check the brakes release. Yeah, and so on and so forth. We can then we can check the wheels spin up. We can check that the anti-skid is releasing the brakes and applying the brakes. Yeah. If you get involved in that test, it's just a matter of spinning the wheel sensor and stopping suddenly, and you can hear the you can hear the hydraulic pressure releasing and applying on the brakes. Yeah, and a warning light will illuminate if the brake system isn't. Sorry, if the anti-skid system's not working. Excuse me 1 second. Can you just give me 1 minute? I've just had a really important email come through from the management. Just need to quickly read it. In fact, do you want 5 minutes now? While I read this.
Okay, Jim, let's have a short break.
Yeah, we'll have a short break. Yeah, I make that 14:22, so we'll say 14:30. Yeah, we'll just have a very quick break and then we'll carry on.
Okay, Jim.
Okay.
Right, everyone there. So the next bit we need to look at then is the retractable landing gear. Yeah, we've looked at the basic landing gear. Yeah. What we're going to do now, we said that with a small light aircraft, having the gear just sticking down into the airflow, yes, it's going to produce a drag penalty, but because of the speed of the aircraft, it's not going to be anything too dramatic. With our larger aircraft and faster aircraft, that drag penalty would be too much. So what we want to do is to pull the gear up into the aircraft, give us that streamlining and that nice aerodynamic profile, so we can achieve higher speeds with lower drag. Getting the gear up into the wheel well, as it says there, we need some sort of powered system to pull the gear up. So we can use hydraulic or electrical power. It says in some simple systems, manual operations used. Yes, it's quite possible, but again, the only time I've seen manual in operation personally is for lowering the undercarriage, which at the end of the day is what you want to do. If you've got a problem, you want to get the gear down. Yeah, we're going to have a manual reversion for that. I've not come across personally an aircraft with a manual means of retracting the undercarriage. That's not to say they don't exist, but not in my experience. Yeah, so the retractable landing gear system, yeah, there's certain requirements that we need to ensure in the retractable system. The fact that we can lock the undercarriage in the up and the down position. Yeah, so it doesn't matter what the aircraft's doing, it's locked and it's not going to shift. We need to tell the crew where the undercarriage is, because they're not the brightest things in the world, are they? So we'll put some sort of indication system in to tell the crew where the undercarriage is, whether it's up, whether it's down, or whether it's somewhere in between. As with every system, yeah, we want backup there. So if we do get a failure, we want to be able to lower the gear. So an alternate method of extending. A means to prevent retraction with the aircraft on the ground. Yeah, last thing you want to do is to be able to select the gear up, aircraft on the ground. And a means to guard against landing with the gear in the up position. So again, protection against the crew landing with the gear up. And it says method of sealing the wheelbase to reduce drag. Yeah, that's generally going to be by doors, but not on every aircraft. Yeah, sometimes they can seal that off aerodynamically. What else we got on there? Yeah, we'll have a shock absorber. Yeah. The main leg's supported in the trunnion, fixed to the strong points on the fuselage or the wing. Shock absorber, yeah, braced longitudinally by the drag strut, yeah, to cope with the fore and aft loads, and the side strut to deal with the side loads that might be present. Torque link is going to prevent your twisting loads. Yeah, and keep the gear stable. So once it's down and locked, it's a nice stable unit, and it's going to absorb the various loads it's subject to. It says in some designs that the drag strut or the side stays in two parts and hinges about the center point, which allows us to retract the undercarriage. So we can use that as a locking mechanism. We can break it and then retract the gear. Yeah, others, the retraction drag operates are an extension of the shock absorber housing. We'll quite have a look at that. Yeah, locking the gear in the up position. Yeah, pardon me. So where we're going to take the hydraulics from? Yeah, from the engines. We said about a reserve system, a backup system. Smaller aircraft, we can use an electric pump to retract and lower the undercarriage. Yeah, but once it's up, it needs to be in the locked position. And the simplest, easiest method of locking it is mechanically. So we're going to lock it in the up position. We're going to lock it mechanically, and we're going to release that lock hydraulically. And the way we do it, dead simple, a little latch that engages with a roller on the undercarriage leg. So the undercarriage comes up, the roller engages with the latch, and a spring pushes the latch over and holds it in that locked position. If I want to unlock it, I need to overcome this muckle great spring, and the only way I'm going to do that is with hydraulic pressure. So we select down, hydraulic pressure acts on a piston, which pushes the lever over, which overcomes the spring. Now the gear is unlatched and it's free to extend. Yeah. So the typical uplock unit, mechanical lock released by fluid pressure, spring-loaded latch attached to the airframe, engages on a pin on the undercarriage, mechanically latched one way and hydraulically unlocked. Ta-da! Likewise, the down lock, yeah, once the gear's down and locked, again, we need that to be physically, mechanically locked, and we do that by over-centering the leg, yeah. So mechanical lock operated by movement of an actuator piston rod. I'll go through that lot in a minute. Locked in the down position, yeah, it's a mechanical overlock. Yeah, the only way we're going to break that is by using some sort of powered means, hydraulically in this case. And what's happening here? We've got a little plate, yeah, a little pin on it, engaged in an over-center mechanism. Yeah, when we select the gear up, yeah, the down lock will it'll pull up in this little groove, which will allow the overlock to unlock. And by using this little plate mechanism, yeah, as we pull the latch up, yeah, it moves up in that groove initially, and then that allows the over center to break. Yeah, so locked in the down position, the catch pin, the actuator piston rod, both at the bottom of the slots. Initial movement of the actuator when the undercarriage up selected, the actuator piston redoors the pin backwards. Doesn't move the radius rod until it reaches the upper end of the slot. When that occurs, catch pin's disengaged, knuckle joint breaks, and further movement of the actuator raises the radius up rod. Yeah, so all we're doing is pulling this pin initially, which is going to pull the catch pin up its slot, and now that's going to allow the lock to break and the leg to fold as it's retracting, or allow the leg to retract, I should say. Undercarriage down selected, the uplock disengaged, undercarriage falls under its own weight, or hydraulically controlled to the down point. Final movement of the actuator moves the catch pin into the slot on the radius rod and locks the undercarriage down. Yeah, so the actuator extends, pushes that pin down, which pushes the catch pin into the bottom of its slot. Yeah, so now it's physically locked in the position. All okay with that? Yeah, so we've got mechanically locked up the way and mechanically locked down the way. Just to run through the sequence, we've got a retraction actuator somewhere on there. We've got our drag brace, we've got our side stay, we've got our uplock, we've got the door, rollers on the door and on the main gear. Aircraft takes off. Yeah, gear extends. Yeah, uplock. Sorry, door lock disengages. Door opens. Yeah. Can you see the actuator there? You see how that breaks that overlock, that over center mechanism. Yeah, as it breaks the over center, now we can start to bring the leg up. Yeah, so over center breaks. Yeah, retraction actuator pulls the leg up. Yeah, the side strut folding in the middle, and the gear up, and then the uplock engages. Obviously, sealing the undercarriage bay for drag. The doors will close and they'll be held in the lock position. Reverse the sequence. Yeah, select down. Doors are going to open. Uplock will release. Yeah, you can see the piston's pushed it over. The uplock's released. Undercarriage is going to fall. Yeah, falls to its down position, and then again we go through that over centering process for the down lock. So it's now down and latched, and it can't unlock unless that down lock's physically disengaged, and then the door will close again. Easy peasy, lemon squeezy. So there's just to again just go through the notes, just make sure we don't miss anything. To reduce drag on the aircraft during flight, landing gears retracted, fed using doors normally operated. Sequencing, we talked about sequencing valves before, and the undercarriage system is going to be sequenced using sequencing valves. That is a physical contact between components to make sure that everything happens in the right order. So before the undercarriage can come down, the door sequencing has got to have gone through its process, and the door sequencing valve will then allow fluid to travel through the undercarriage actuator, and that way we can't drop the gear through the door or retract the gear up through the door. So the door has physically got to be open before the cycle can continue. Yeah, once the leg's locked up, the door will close to fare the undercarriage, and the down cycle works in the same way. Doors open, leg down, door closes. Sequence valve, plunger operated valves, and we saw those the other day. Ensure that everything happens in the correct order. Yeah. I think this slide's a bit out of line with the text. I was trying to see if I've missed the bit on the ground locks there. Yeah, ground locks, I'll maybe come back to it, but ground locks are essential to prevent retraction of the undercarriage while the aircraft is on the ground. Yeah, so when the aircraft lands, unless it's going flying again straight away, we need to put ground locks in. And the ground locks physically lock the gear in position. So even if we make a selection, yeah, the gear can't retract. We might come back to those. I'm not 100% sure. Hopefully we will. Your sequence valves, exactly as we said the other day, it's a mechanical contact. In this case, a little plunger. Yeah. Outline to the undercarriage downline, fluid pressure coming in. Yeah. Pressure to the door jack. Yeah, and pressure sits in the sequence valve waiting. As soon as the door opens, yeah, strikes the plunger pushes the valve open, and that allows the hydraulic fluid to flow through off to the undercarriage leg, and then the retraction sequence can or extension sequence can begin, whichever it may be. Yeah, again, we don't need to know the ins and outs, but we do need to know that sequencing valves are needed to make sure that things happen in the right order. We do need to know that there's a mechanical up and a mechanical down lock, and they are released hydraulically. Just for your sequence valve, yeah, you supply in, yeah, and your hydraulic pressure is going to be waiting at your your actuators. Yeah, the line continues off elsewhere. Yeah, so your pressure weight in there. As your undercarriage retracts, yeah, the actuator travelling that way, and as it does, it's going to open the sequence valve and allow oil through the door actuator. Yeah. So now as you go up, yeah, sequence valve's opened, flow through at the door actuator. As the door actuator closes, it's going to close that sequence valve off. Yeah, so now we go on to the return journey. Yeah, want to lower the undercarriage. Yeah, allow pressure in. Yeah, pressure into the door jack, and as the door jack extends, it's going to open the sequence valve. As the sequence valve opens, it's then going to allow fluid through to the downline. Yeah, so that contact has physically got to be made before the next step in the sequence can carry on. And you can see as the undercarriage goes down now, the downline, the sequence valve's closing. So when we go back, yeah, that sequence valve's shut until the next part takes place. All okay with that? Sequencing. Ding, ding, ding. Happy days, yeah, we've been there, done that, so we know what sequencing is doing. The walking beam, yeah. Remember the other day when we did flying controls and we saw that reaction link? Yeah. Well, the walking beam is very, very similar, in as much as the walking beam is there to prevent a build-up of stress on one particular point on the structure. Reduces the reaction force going into the structure from the main actuator. Your main actuator mounted on the structure, yeah, for every action, equal and opposite reaction. So that the mounting point is going to take an awful lot of stress. Yeah. So what we do is we put a walking beam on, and the walking beam via a link, yeah, just moves as the undercarriage is moving. So the undercarriage up and locked, yeah, the walking beam tucked away. As we lower the undercarriage, yeah, as the undercarriage starts to lower, now this little link at the top is being pulled round by the actuator, which in turn is pulling the walking beam as it clicks round. Yeah, so now we're sort of the stress of the actuator extending and retracting. Yeah, that stress build-up there is being transferred back through the system. So rather than having one area of big concentration, what we're doing is just sharing the load by using that walking beam and that little link as it kicks around. Yeah, so highlighter at the top of page 153. The walking beam serves to reduce the reaction force going to the aircraft structure from the actuator. And then it just tells you how it works. Yeah. Like I say, yeah, it's just a little bracket attached to the leg as the gear extends. Yeah, as that end's pulling up, this end's pushing over, and it's just recirculating that load. Everybody okay with that? Any problems there? Oh, easy peasy, brilliant. Lots more pictures, and then we come on to position indication for our undercarriage. Electrical indicating system tells the crew the position of the gear. Yeah. Normally consists of microwaves on the up locks and the down lock, micro switches on the up and the down locks, which make or break when the lock's operated. Connected to a position indicator, and the Flight deck, yeah, mechanical indicator may also be provided. We'll look at that later on. There are various types of indicator. Yeah, the one I'm about to show you is the favoured one, and it's the one that is displayed in the notes. Yeah, this one, nice and modern. Yeah, red light for unlocked, green light for locked. Yeah, down and locked. The most common type of indicator, the one that I've come across most British aircraft use this type of indicator, and it's dead easy. You know, there's no discrepancy in it. It's just a dial indicator with 3 windows at the lower part, 3 windows at the upper part. Each one of these indicators is a little bulb. Yeah, we've got 3 green bulbs at the bottom, which indicates that the undercarriage is down and locked. In each of the indicators, there's 2 filaments. So if we get a failure in one, the other one's still going to light up and not give us a false indication. There's a press to test facility, so we can check to make sure that all the bulbs are working, all the indicators are working. And the other thing we have on the dial is a day-night switch, a dimmer. So at night, yeah, the lights are dimmed down. They're not as bright and not as blinding. Yeah, so we'll start off with the sequence. We've got 3 green lights. We select undercarriage up. As soon as the undercarriage or any one of the undercarriage units goes away from the locked position, the down and locked position, a red light comes on. Yeah, I should have pointed out, obviously, that each light corresponds to an undercarriage leg. Yeah, so your left leg, your right leg, and your nose leg. So as soon as we go away from the locked position, we'll get a red light to tell us that the undercarriage is unlocked. Once we're up and locked, all the lights go out. Yeah, we lose all the lights. Yeah, lose all the lights. If we've got one leg unlocked and 2 locked down, 2 greens and a red. Yeah, again, as soon as we come away from the locked up position, the red lights will illuminate. As the gear comes down, as it locks into position, the green lights will illuminate. Yeah, so it's fairly straightforward, fairly simple. Just remember, down and locked, all green. Red light means that the undercarriage is away from the locked position. In the notes, it says it's in transit, but it could be not locked down properly. So as soon as you're away from the locked position, red lights, and then when we're up and locked, all the lights are out. Other types of aircraft, as we saw on the previous slide, might use slightly different, but this is the one that it goes on in the notes, describes in the notes, and in all honesty, it's the one even on modern aircraft that I've come across. Yeah. It's simple and it works. Safety features in the retraction system. And again, for some reason, I did have all these, but my slide seems to have been corrupted. Safety features in the retraction system. I'm on page 156. The nose wheel centering. Yeah, to avoid damage to the airframe structure, nose wheel's always aligned in a fore and aft direction during retraction. And one of the methods that we looked at was the cam and the cam track inside the nose leg that we saw before. Yeah, that's all it's telling us. Safety device incorporated prevents the inadvertent operation of the undercarriage lever when the aircraft's on the ground. So what we've got with the undercarriage handle, there's a safety lock built into it. Again, the one it's describing is if that's your undercarriage selector handle, yeah, mimics the the wheel, a wheel-shaped selector handle. Why is it wheel shape? Module 9. Yeah, on the selector handle, there's a little lever on the top, and that little lever is connected to a solenoid inside the handle. To select the undercarriage up, you've got to push that little lever forward, which disengages the solenoid, or engages the solenoid, one of the two, whichever way around it is wired in. Once that solenoid has released the handle, then we can make an up selection. Yeah. So while the aircraft's sitting down on the ground, yeah, to prevent accidentally knocking the handle or whatever, there is a safety device built in. Yeah. Struts compressed, switch is open, strut extends after takeoff, switch contacts close. Electrical supply to the solenoid complete, so releasing the selector lever lock allows the landing gear to be selected up. Yeah, so once we're up off the ground, we can just select. Yeah, means of overriding the lock, so a separate gated switch could be provided in case anything goes wrong. Other methods you've got, if that's your handle, you're looking forward at the gear lever, a detent, yeah. So your undercarriage is selected down, that's up, yeah. If I'm in the down position, yeah, I've got that little detent there. I've got to physically move the handle out of the detent to push it up. Yeah, if I'm in the down position, that's fine. It'll live there. Yeah. So, do you know what I mean by the detent? Yeah, it's just a little groove in the selector channel, and the handle is latched into it. So to move the handle, I've physically got to move the handle over and then up. Yeah, and again, it's to prevent accidental operation of the lever on the ground. So that's your safety lock. Means of overriding the lock, separate gated switch. Yeah. Maintenance, landing gear performs an important function, and we've got to follow the AMM instructions for any maintenance that we perform. Ground locks, we've already mentioned ground locks. Yeah, if the aircraft isn't going flying, then the ground locks should be fitted to prevent that inadvertent, or if anything went wrong, it's not likely to fold. Any replacement of components, any adjustment of components, we need to do a retraction check. Common sense, don't take anything out while there's pressure in the system. Blank hole pipelines, inspect components, none of that is relevant to what you need. Routine servicing, yeah. None of that is relevant to what you need. Yeah, if you're broken into a system and you're doing a functional check on it, just bring the gear up slowly for the first retraction, check everything's all right, and then you can do it at regular speed after that. Yeah, tells you about putting power on, checking clearance. Again, you're probably all aware of it, but if you're jacking an aircraft to do retraction checks, make sure it's clear enough of the ground so that the gear doesn't catch on its down cycle. That's happened before. Make sure it's high enough up in the air. And that was that for our retractable undercarriage. Has anybody got any questions on that at all? Retractable undercarriage? No? Lovely. Right, well, we're going from there then into powered steering. Yeah, a means of steering the aircraft on the ground is required, certainly for larger aircraft. We're going to use a powered steering arrangement where the nose wheel's turned by hydraulic, pneumatic or electrical power. We're going to drive it from the cabin, and we're going to do that by either using a tiller, a steering wheel, if you like, in the cockpit, or some aircraft we can use the rudder pedals backwards and forwards to steer the aircraft. Again, your larger aircraft tend to have a steering handle in the cockpit. Again, you can see here how tight the turn is and how much strain is being put on the undercarriage legs. So we need to be pretty careful, make sure that we stick within turning radiuses and all the rest of it. Yeah, just we're going with that. Yeah, components in there then. Yeah, we're going to have a steering wheel. We need a control valve. Yeah, to tell us which way we're going. Yeah, steering cylinders to move the nose undercarriage, and some sort of follow-up device to hold the nose wheel at the right angle until we reselect it. Yeah, so if I turn the tiller, the steering wheel, yeah, I want to maintain that degree of movement until I put another input in. This lot is just an example of a nose wheel steering system on a nose leg. We looked at we know why we've got the drag strut, the shimmy damper. We've mentioned the shimmy damper, and another method of preventing shimmy. We've got the two nose wheels there. Steering bypass valve. We'll come on to that in a minute, and a steering valve itself. And the steering valve is going to tell us which way to go, drive the gear. Steering actuators themselves, yeah, just little jacks that will move the legs left or right, and your sort of feedback mechanism all covered in a nice cover to keep it free from all the dirt and the grime and the crap that floats around. Aircraft I worked on, we used to have terrible problems with moisture ingress in the nose wheel steering in the motor, and we were forever having to replace motors, and it was a real pain in the arse job, just because of the environment it was in, and they weren't weatherproofed properly by the manufacturers. So yeah, good protection. You know, if you get problems with them, have a look, make sure you're not got moisture coming in. How it's going to work then? We've got the steering wheel in the cabin. Yeah, steering wheel in the cabin, and that's connected via pulleys to what they call the steering drum. Yeah, steering drum again via sort of cables attached to a little beam assembly, and as I move the drum backwards or forwards, that's going to pull this beam left or right. As the beam moves, it's operating a steering control valve, and the steering control valve is just going to direct hydraulic pressure into one actuator or the other. If I direct it into this actuator, then that actuator will extend, this one will retract, and vice versa. If I go the other way, that one will extend, that one will retract. Thereby, we are moving the nose wheels. Yeah, so main operating pressure from the undercarriage downline, limited emergency supply from the accumulator. Pressure passes through a changeover valve, which ensures that the steering system is only in operation when the undercarriage is down. Yeah. We don't want it working in the air. We don't want it wedging in the air and having the wheels off centre in the air. Pressure directed through the control valve to the steering jacks. Yeah, so downline pressure, yeah, control valve into the steering control valve. So pressure directed through the control valve, changeover valve to the steering jacks. Changeover valve, downline pressure, changeover valve to the steering control valve. From the control valve down to the actuators or the jacks, which retract or extend to the limit. Yeah, extend or to rotate the nose shock strut within its housing. Yeah, movement of the steering wheels transmitted through a mechanical linkage to the control valve, depending on how much movement we want. Follow-up links from the nose undercarriage reset the control valve as we get to the selected position, and when the selected angle is reached, we cause a hydraulic lock in the valve. So we're going to stay in that position until we reselect it. So theoretically, you could just go around in circles. Yeah, steering's released. Control valve will return to neutral under action of its centering springs. And the nose wheel's then free to caster. Inner cylinder in each steering jack is connected to the undercarriage upline, supplied with fluid under pressure when the gear's selected up, and that ensures that the thing steers to centre and stays in the midpoint. Yeah, bypass valve allows fluid from the steering jacks to go back to return. Yeah, so changeover valve, downline pressure, into the control valve. Yeah, your input that we saw on the previous slide, moving the selector and the selector directing fluid to one side of a jack or the other. So if it comes down this way, it's going to push that jack that way. It's going to push that jack that way. We're going to turn the wheels, and obviously the return fluid is going to go down through the bypass valve and off to return. Yeah, hold the tiller in position. Obviously that control valve is going to remain in position, so we're just going to get the selected amount of movement. If I release the tiller, yeah, again with a spring in it, springs in the jack, what's going to happen is that'll go at the neutral position, and we're going to get fluid directed into the actuators, so you've got exactly the same amount of pressure in both ends of the actuator, and it's going to cause the actuators to steer back to centre. And then obviously the return lines via the bypass valve off to return. So yeah, dawdle along, turn the tiller, operate the valve, steering valve. That sends fluid down to the steering jacks. The steering jacks will turn the strut. So long as I keep my hand on the tiller, that input will remain. Take my hand off the tiller, everything will steer back to a central position. Everybody okay with that? Any problems there? Pictures. Castering. Yeah, when the control valve's in its neutral position, fluid is free to flow between the steering jacks, allowing the aircraft to be towed or the nose wheels to return to the centre position, as we've just said. Angular movement of the nose wheels during towing will be transmitted through the follow-up linkage to the steering wheel. So some form of quick release pin provided to enable the steering jacks to be disconnected, so that the noses we can turn it through larger angles. Yeah. So with the nose wheel steering, there will be a method of disconnect, be it a pin that goes through the linkage, disconnect something, or whether we've got a special key or whatever. We can disconnect the nose wheels, and once the nose wheels are disconnected, we've got a much larger range of movement. Yeah, if we do use a disconnect device, just make sure it's got a pennant on it, and it gets removed after the towing operation has been completed. Page 165, it's worth remembering that on large wide-bodied aircraft with multiple bogies, the body-mounted landing gear bogies are steerable in a similar way to the nose wheel. So that direction degree of turn corresponds to that of the nose gear, the two systems are interconnected. There's a steering interconnect. Position of the nose wheels relate electrically to the body gear, and the body gear will take up the same position as the nose wheels to give us a better turning rate, turning circle, I should say. Yeah, unfortunately, that doesn't run. Again, it was a YouTube video. Aircraft was in and parked. Another one comes from the side. Because the apron's absolutely soaking, he starts aquaplaning. He can't brake, and he just plows straight into the back of this little aeroplane. Again, I'll try and find it for you later on. If I don't, I'll see if I can find the link and send it to you. But it's quite entertaining just to watch the two aircraft collide. Good example of aquaplaning. Maintenance of the steering system, yeah, found in the AMM, yeah. Make sure we adjust the linkages properly. Any incorrect rigging, you're not going to get the right steering range. Left and right are going to be out of alignment. Rigging pins, if we use those, make sure that they're documented and removed before we do anything. Cables, tension using tensiometer. Nothing we need to work there. Functional check, yeah, we can do functionals. If you are doing a test of the nose wheel steering, if you're doing it on the ground, make sure you put some polythene bags or what they call skid plates under the nose wheels. Skid plates are just 2 sheets of aluminium alloy with grease between them. Tow the nose wheels onto the skid plates, and then when the nose turns, it's turning the plate. You're not rubbing the tires on the ground and damaging the tires on the nose leg. We can check it in the air to make sure that everything steers to center, but again, the functional check is going to be detailed in the maintenance manual. Yeah, I don't think there's anything there we need to worry about. Yeah, centering cams, yeah, so what we do, got the aircraft on jacks, we'll put the nose wheels in a off-center position, and then when we select undercarriage up, the nose wheels should steer to center before the undercarriage retracts. Nothing there to worry about. Anybody got any questions at all on anything there? Anything at all?
Hello, Jim.
Yeah.
Just a minute. I didn't get this walking beam arrangement. Is it important to go through this sequence? Or
not so much the sequence, but you need to know what the walking beam's there for.
Okay. So the sequence, because there are few complex paragraph here, and with the main gear, like the backing maintenance and log is about slightly inward of the Tunian center line. So I'm not getting these things.
Say that again. I'm talking. Are we talking about the walking beam still?
Yes.
Right. So
Yes.
the walking beam, yeah, is connected from the where the main actuator is mounted on the aircraft structure. Yeah, every time that actuator extends or retracts, there's going to be a reaction force on the attachment point on the aircraft structure. Yeah.
Okay.
You agree with that?
Yes.
Every action has an equal and opposite reaction. So as that's pushing on that leg, it's also pushing on that attachment point. So there's going to be a lot of stress builds up there over a period of time. So to relieve that stress, they put the walking beam in, and the walking beam is just connected to a little link on the undercarriage leg. So now, as I've got the undercarriage up and locked, yeah, the beam's pulled over that little link. Select undercarriage down, and now as that actuator's extending, yeah, the walking beam the actuator is retracting, yeah, to bring the gear down. Yeah, as that actuator is retracting, that walking beam is pushing on that lever. So that lever pulling that way, pushing that way. So now when the gear is down and locked, yeah, that the actuator is fully retracted. It's pulled that link round, and what's happening as the gear's moving, the stress that's being built up here by the reaction force is being transmitted round in a circle, basically. So we're relieving the stress that's building up at one point, and that's all the walking beam's there for. Yeah, and I think it was the very first paragraph that said that the walking beam is there to relieve the stress of the reaction forces, and that's the bit that you really need to know.
Okay, Jim. Okay.
Yeah.
Okay, Jim. Thank you.
Was that it? Anybody else? Right. We'll go through a typical landing gear retraction system then. Yeah, we're motoring along quite nicely. So what have we got then in the cabin? Again, your basic controls. Start with where we are. We'll start off the nose wheel steering tiller. Yeah, just a steering wheel for the nose wheel steering. Just behind that, the nose wheel steering switch, so we can kick it in. Brake temperature selector, we've talked about those. Parking brake handle will be in there somewhere. Landing gear bay overheat. We kind of mentioned that when we did protection, but we'll maybe come back to that one. Landing gear selector lever. Yeah, so landing gear up or down, so we need some means of selection. And then in this particular instance, we've got a emergency uplock release for the nose gear. Landing gear changeover control, we've not mentioned that, we don't need to. Position indicators, horn cancel. Yeah, if you get a problem, you're going to get the warning horn, and a brake pressure indication, a cockpit layout. Why the fuck that's in there, I've got no idea. Yeah, system described. Undercarriage doors are mechanically operated by the landing gear movement, so we don't need to worry about separate door system. Normal retraction and lowering achieved hydraulically. Landing gear locks engaged mechanically, unlocked hydraulically, normally. Uplocks released manually from the control cabin should be the failure of the complete system. Landing gear position and lock position shown by indicators in the cabin. Mechanically operated indicators provide confirmation that the down locks are engaged. I'll show you those in a minute. And somewhere on there, the undercarriage is going to have restrictors in it to restrict the speed at which it's lowering and sometimes raising. So we're not creating big shock waves through the airframe. So those are the indications they're using for the system described, which is fairly generic. Yeah. The different selections, yeah, you go through your selector valve. The selector valve changeover valve where we're coming from, up or down. Yeah. So undercarriage up. Yeah, we've selected, gone through the selector, down to the up locks, pressure waiting at the up locks. Yeah, and the other side of the up lock, obviously open to everything open to return. We're going to have sequence valves in there. Yeah, so the pressure to the up lock. Yeah, going to release the leg. Yeah, once that's released, then we're going to have fluid down to the actuator. Yeah, and the actuator can start to bring the leg up. Anything else I need to say there? Not really. I don't want to go too deep into that little lot. Yeah. Gear down. Yeah, you can see leg release. Yeah, unlocked hydraulically, and again your actuator pushing down. Yeah, lowering the leg, and again somewhere in there you'll have your sequence valves. Yeah, your changeover valve just letting you know whether it's up or down. Auxiliary just using an emergency system. Didn't really want to go through any of the circuit diagrams, so I'll just stick it back just in case there's anything I miss as I go through. Normal landing gear selector lever located on the instrument panel. Lever connected to the normal landing gear selector valve by a control cable. Selector valve directs pressure to unlock and operate the landing gear. Selector lever is gated in the up and down positions. That's the D13 to make sure that we can't accidentally move it. Locking latch prevents the lever being moved to the up position while the aircraft's on the ground. Locking latch removed by solenoid operation, which we talked about before. Override switch to remove the locking latch if the aircraft on the ground system fails. Yeah. Restrictors in the upline slow the rate of lowering of the undercarriage. Again, page 170. Yeah, restrictor valves in the upline slow the rate of lowering of the undercarriage. If restrictor valves weren't fitted, the heavy units would fall too quickly and cause jarring, severe vibration, and structural damage. Yeah, so stick a highlighter through the requirement for restrictor valves. Fully down, retracted, the gears held in position by hydraulic pressure. When retracted, landing gears held in position by mechanical locks. Engaged by spring action. Locks are released by small hydraulic actuators on each one. Yeah. Oh, so what we've done, we've got the gear up selection. Yeah, we've got the main supply in through the selector, through the upline, through the changeover valve. The locks mechanically pushed over in the lock position, and then your main undercarriage actuators fully retracted. Again, your restrictor, and the same on the other side. Yeah. Yeah, the mechanically locks mechanically locked. Yeah, through your restrictor, your actuator extended. Yeah, select down. Yeah, select a valve or move, changeover valve shifts. That's going to allow return pressure to go. So now through the selector, into the down line, into the up lock. Yeah, and that will release the up lock. Yeah, and again, pressure into the actuator. Yeah, extends, pushes the gear down, and again your down lock assembly physically engaged. Alternate system. What we're talking here. whatever we're going to blow it down with, yeah, from the auxiliary reservoir, so an auxiliary DC pump, yeah, into the isolator valve, yeah, and again, we're going to allow the alternate stuff to push the undercarriage down. Yeah, the lock's released. Yeah, unlock it, and the gear can come down under alternate pressure. Didn't say anything about that little lot. Alternate lower in the event of failure, normal system, normal landing gear, select valve. Landing gear may be unlocked. Load using the auxiliary system, and the landing gear changeover control. Red painted landing gear changeover handle located on the instrument panel. Not necessarily red painted, but it'd be highlighted. Emergency undercarriage. In this case, it says pulling the handle. Yes, changeover valve connects the landing gear to the up line. Other changeover isolating valve directs auxiliary system pressure to the up locks. Pressures the main actuators via shuttle valves. We talked about shuttle valves the other day. Shuttle valves, I think, are in here, allowing us to use an alternate power source. No, they're not. Can we remember shuttle valves?
Both an emergency and normal use, I think.
Yeah, so you got normal in, out to the system. You've got your secondary supply. Yeah, and you've got a little piston. Yeah, if the system is under normal operation, normal system fluid in through the shuttle valve and then off to do what it needs to do. If we have an emergency selection, yeah, the emergency pressure be selected. That would come in, cause the shuttle valve to move over, seal off the prime source, yeah, and then your secondary or your alternate supply would go off to feed your yeah, we'll go off to lower the undercarriage for us. That's your shuttle valves. Yeah, we can either use an alternate hydraulic source or we could use nitrogen. Yeah, nitrogen to blow the gear down. Some aircraft, we just pull a handle and that disengages the up locks, and the gear will fall down under its own weight. Yeah, so it kind of depends on the system we're using, how we're going to get the gear down. Yeah. In fact, there it says, yeah, once we're down, normal landing gear got to be selected to down. Yeah, change over control handle, part of the reset. Some aircraft provided with a hydraulic hand pump. We can use a hand pump. We select emergency undercarriage and pump like buggery, and that will lower the undercarriage for us. Another method allows the undercarriage to free fall in the event of a hydraulic failure. Yeah, uplock handles or the uplock release handles are operated. The uplock's release, and the gear will fall under its own weight. But when we pull those handles, we've got to allow the return fluid to go somewhere, so that the part of the mechanism opens up the back of the actuator to return, so we don't get a hydraulic lock. And as I say, nitrogen or compressed air, it says in the notes, but normally nitrogen may be used as another method of emergency lowering. Door sequencing, yeah, we mentioned sequencing, and again, that's just on that, on this thing, it's showing the various valves. Nose jack, nose lock, main jack, main lock, LJ lock jack. Yeah, SV, I think, is selector valve, door jack. Yeah, so going through the sequencing, just remember that everything is sequenced to make sure that it happens in the right order. Yeah. It then, and I don't propose to do it now, it just goes through an example system. So the picture you've got on page, whatever it is, page 177, it just takes you through the sequence of what's going on, how everything's happening. Yeah, so landing gear selector moved up, fluid pressure directed up, fluid to the sequence valves, retraction jacks, all the good stuff. If you want to follow that through for your own enjoyment, please do. But we don't need to worry about it for what we're doing. We need to know how the general system's operating. We need to know that the locks are unlocked hydraulically, locked mechanically. We need to know we've got emergency provision. We need to know what the indications are. And again, did I say highlight the indication bit? Yeah, what the indicators are and the sequence of indication, you need to know that. What else do you need to know? The fact that we've got to fit ground locks when we're not in use. That there's a safety mechanism in the handle to prevent inadvertent selection on the ground. It's a D13 or a solenoid in the handle normally. What else? The walking beam we've already been over. Yeah. Just let me go back to the start of this. I just want to make sure that I've covered it all. Yeah. So retractable landing gear, mechanical locks. Yeah. Indicators. You need to know about those. Safety features. You need to know about those. So how the gear is unlocked, locked mechanically, unlocked hydraulically. Mechanical, it's an over-center mechanism that's undone hydraulically. The sequencing, make sure we know that sequencing happens. Yeah, so everything moves in the right order. Ground locks, we've talked about the importance of ground locks. The sequencing valve, a physical connection. Circuit diagrams, what's going on. The walking beam, I've been over that, so we know that that's to relieve the reaction stress, protect the structure. The indication, you need to know the sequence of indication. So 3 greens, 3 reds, all out. Anything away from the locked position will indicate red. The steering system, yeah, how we're going to move left and right. Yeah, your powered steering. And that with your powered steering, yeah, it's going to bring the nose wheels back to center when there's no input on them. Castering is the disconnect, and that allows the wheels to move in a much larger radius, so that we've disconnected the steering mechanism. And we looked at retraction. Yeah, the retraction system, and just how it works. Yeah, and the fact that we can lower the undercarriage in the case of an emergency, and the various methods of doing that. We had a look at that. Position indication, again, green lights indicate that all are down and locked. The red lights will come on if the doors are not closed with the gear up. Any throttle is retarded to idle with the gear in the up position. Yeah. What we're going to have is a means of preventing us from landing with the gear in the up position. So if you've got the throttles at idle and the gear's up, yeah, you're going to get a warning light there. During transit, yeah, or when any landing gear is not in the position that corresponds to the position of the handle, we're going to get the warning. And all your lights out is when the gear is up and locked and the throttles are away from idle. That landing gear handle with the throttles, the ones that I used to work on had a flashing light in the undercarriage handle. So if you had the throttles at idle and the gear was up, the light would be flashing. Move the throttles away from the idle position, the light would go out. Yeah. And that was to warn you against landing with the gear down, the gear up. Sorry. Yeah. Electrics. I'm not gonna go through that little lot. Some aircraft, you've got mechanical indicators as well as your electrical indicators. So if you have a power failure, you want to know what position your gear's in. There are little windows that you can look at from the cabin and see a little indicator flag that will tell you what position the landing gear's in. Yeah, it's just a little flag. It's connected to the leg, and it'll pop up in the window if we're down and locked. This sort of thing. Yeah, you're all up. Everything nice and sweet. Yeah. Up and locked, all doors closed, mechanical indicator nice and flush. Yeah. Gear's up, but we open the doors. Yeah. Doors fully open, gear comes down, gear locks down, and then the mechanical indicator will pop up so we can see the position of the landing gear. It's just to give you an idea of what's happening in the sequence. Anything else there that I've missed? Door sequencing. We've talked about that. Talked about that. Position and warning. Yeah, we've just done that. Please make sure you know the indication sequences, and please make sure that if the throttles are retarded, yeah, the gear's in the up position, you're going to get the red lights. And that light will go out if you move the throttle away from the retarded position. It's just to prevent you landing with the gear up. Landing gear door positions monitored by quite often proximity sensors, contain no moving parts, and just work on attraction as the two halves of the sensor come into contact with each other. Put a light on, or when they brake, it'll turn the light off. Only thing with proximity sensors, I've never used them, but I'm told that they're quite prone to failing because of dirt accumulating. So we need to make sure that they're kept clean. Audible warning, yeah, if we're not in a safe condition. I said that we're going to get the whoops and boops to go with the position indication. Oral warning, actuate if the gear is not down and locked, engine power reduced to idle, and if the aircraft's below a predetermined speed. All warning may be silenced. Oral warning actuated if the landing gear is not down and locked when the flaps are extended beyond the approach position. So some aircraft you can actually tie that into the flap position. So you've got to have your gear down before you can complete your flap manoeuvres. Yeah, it stops you landing again with the gear up. Indication, not worried about that. The sequencing of the lights on page 180, yeah, just showing that 3 greens, all down and locked. Yeah, take off red lights, show that we're unlocked, and then all lights out once we're up and locked. Gear visual position indicators, we've just been through that. Yeah, some aircraft have little mechanical flags that will pop up and show you what position the gear's in. Yeah, and you can see those through little viewing windows. Yeah, and the indicators confirm the gear's down and locked. Happy days there, and we've just had a look at that. Shuttle valves I've mentioned, emergency lowering I've mentioned, blowdown. The last little bit are the WOW switches, the weight on wheel switches. Yeah. Flight and ground sensing control mechanism provides the mechanical means of establishing a ground or flight mode, and the various systems can then kick in or trip off or whatever they need to do, depending on the position of the WOWs. The one described in the notes, yeah, is just a little mechanical linkage. As the leg extends, yeah, it pulls down on a lever, and again that's pardon me, attached by cables to the sensing mechanism. Yeah, when the legs compressed, again the mechanical linkage will compress, and that'll click the cable over to and give the opposite sense for the WOW sense. Yeah. So you see what I mean? As the leg extends, yeah, it's going to pull down on that link. As that link pulls down via the linkage there, it's just going to move that little quadrant. Yeah, leg compresses. Again, linkage will compress with the leg, and again the quadrant will just move in the opposite direction, and that's going to tell the aircraft whereabouts it is. Is it on the ground or is it in the air? Yeah, so nose gear strut extends, nose gear upper torque lock draws the linkage down, pulls the spring-loaded rod down and rotates the cable sector, what I've just called the quadrant. Yeah. Same time, the ground control relays are actuated, causing various electrical circuits to kick into the flight mode. Struts compressed, ground mode's established, pedal steering systems actuated to permit rudder steering. Anti-retraction latch engaged to prevent the undercarriage being operated, and the various features there. Obviously, that's fairly, should we say, antiquated. Probably the more modern, and the bits that you'll get used to are the WOW switches, the micro switches that are located. Yeah. So as the weight of the aircraft hits the ground, yeah, the micro switch is going to make and send the relevant signals to the ground sensing system, or whatever they're going to call it. Yeah, so your WOW switches, sometimes called ground sensing switches, sometimes called squat switches, all the same thing, just different terms. Yeah, so well, the weights on the landing gear, the switches won't allow the gear to be retracted. They'll trip off, what systems did we say? It'll change over the toilet heater. It'll prevent the stall warning from operating. It'll allow the nose wheel steering to operate. It'll go through the various rigmaroles there. And I can't think of anything else. Like I say, your micro switches, your WOW switches, located at the back of the main legs. On this one, it's on the nose leg, and just swap over between systems. There's not a horrendous lot else to say about WOW switches, and that quite nicely. We're about 10 minutes before time, but we didn't have a break this afternoon, and that brings us to the end of landing gear. What I'll do, I'll send out some landing gear questions to Yadav, and he can forward them on. But while we've got a couple of minutes, has anybody got any questions at all on anything that we've done so far? No. I'll stay online for a little while, just in case anybody does come up with any questions. With the B2 guys, that's it from you guys now. I'm just left with the B1.1s from tomorrow for a couple of days. But I did say on I think it was the 3rd of February, yeah, the helicopter guys and if you guys want to come back, I'll make the 3rd of February a kind of revision day. So if there's any questions on any of the subjects that we've covered so far, then please jump in, give me a shout, and we'll see if we can clear up any problems that you might have. To that end as well, I'm in the process of making a Module 11 exam, but it'll contain questions that will be relevant to you guys. So hopefully I'll get that finished off, and I'll send it out to everybody. What I will say with the Module 11 exam, we're not allowed, as I said before, to do MCQ, but what I've done is taken MCQ questions and just turn them into open questions. So as you look at those and you find the answer, yeah, it's kind of MCQ, but just without the options. So they're all relevant. So you know, if you want those, I'll get them to you as soon as I can. So has anybody got any questions, any problems, any queries?
Hello, Jim. Hello.
Yeah, I'm here.
You are telling about the exam set questions, just like 140 questions, but without options.
They're not the exam questions, but they're not a kick in the arse away. Yeah.
For practice only. For practice only, you will be giving like that.
Yeah. But the questions I send out to you won't be far off.
That will be very helpful, Jim. If you give us like a set of one or two sets of that question, 140 questions, but without option,
it won't be 140 questions, but I'm in the middle of writing them, so hopefully I'll get them finished before the 3rd. As soon as I get them, I might even work the weekend. You never know. But as soon as I get them finished, I'll get them out to you.
So, okay, Jim. Thank you.
Okay. Anybody else got anything? Right. In that case, I'll get on. I'll get the landing gear questions sent out this evening. The B1.1s, I will see you at the usual time. The B2s, if you want to join us on the 3rd of February, you are more than welcome. In the meantime, if you have problems,
we will join on 3rd February, sir.
Sorry?
We will join on 3rd February, sir.
I can't hear you.
Sir, I will join on 3rd February, sir.
Okay, lovely. Guys, yeah, that's fine.
Thank you, sir.
Okay. So the B1.1s, I will see you tomorrow.
With what chapter should we go tomorrow?
Oh,
what chapter we will be doing tomorrow, Jim?
That's a very good question, actually. We'll do structures. We'll do the big structures book, which is B11 book 1, I think.
Okay, structure tomorrow.
Yeah, that's a nice easy subject because you've done half of it. We did half of it as part of the combined. Okay then, guys. Yeah, I'll stay online for another 10-15 minutes. If you think of any questions, give me a shout. If not, if I don't see you on the 3rd of February for the B2s, best of luck with your Module 13.
Okay, sir.
All right then. Okay, cheers for now then. Give me a shout if you need anything. I'll still be online even though my picture's going off.
Hello, Jim. Hello, Jim. Are you there? Hello, Jim. Are you there?
Yes, I'm here.
Okay, I'm Chiranjeev speaking.
Hello. Yeah.
So for B2, we'll be joining from February 11, right?
Just give me 1 second. Can you see that okay?
Yeah.
Right, so the B2s, yeah, you finished with me today. And then from the 4th to the 16th of February, what are you doing there? B1, B1.3, 4th to the 16th of Feb. Yeah, you're doing that module there, which I think is the avionics stuff, avionic electrical stuff.
So 4 to 16.
That's what it says on here. 4th to the 16th, yeah. And that says B1.1, B1.3, and B2.
4 to 16. B2. Okay. The given schedule from NAAT, it's 28th January to 3rd February. There is no class for B2.
No.
And from 4th of February to 10th of February, there is no class for B2. So it's been changed here, right?
Well, yeah, check. You'd have to check with Nat, but I'm going off the planner that I've got.
Okay, then February 13 to 4th March of 4th, March 4th, there is no B2 class. Okay.
No B2 there.
13 Feb to 4th March. No B2. And then 5th to 31st of March. Okay. So we have finished the first part, right? For B2.
Yes.
For 80 questions.
Whatever it is, yeah.
Okay, thank you, Jim.
Okay then. Like I say, I'll try and do a recap on the 3rd of February. So if you want to join us, you're more than welcome. If not, all the very best with you.